Today, we're going to go a little bit more deep into caches. This is an area where a lot of work has been done for many, many decades. As I mentioned last week, the earliest cache paper was in 1962, right? That's 60 years ago. But much better. That's 60 years ago. And over the course of 60 years, a lot of work has been done and a lot of different things have been explored. I'm just going to give you a glimpse of it today. There are a lot of design decisions in the memory hierarchy. This is one of the most complicated parts of a system today, how to do the caching. And it keeps getting bigger and bigger, as we discussed earlier. So you'll get a glimpse of it, but know that there's a lot to do when you're implementing a cache hierarchy or memory hierarchy in a real system. Okay, so hopefully you know about the extra assignments. These are the same readings that I've been showing for many days, let's say. And just to jog your memory, this is what we're talking about, the memory hierarchy of a modern processor. We'll keep talking about that until the end of the semester. And this is another example of it that includes the registers as well as the solid state drives today. I should mention that this memory extends. So this is, if you think about it, this is a single node. A single node has this memory hierarchy and then a storage unit and then main memory, as you can see over here. But this memory, don't think that this memory is just for a single node. In modern data centers, for example, or servers, you can extend the main memory hierarchy beyond the single machine. So in some cases, you need to store much more data than what you can do attached to a single node, like this node, let's say. So what happens if you actually need more data to store? Then you actually go to some other machine. And this could be an example, basically. You could have a compute node over here that's local, and it has its own local memory and local hierarchy for memory. And then you attach some remote memory node, which could be essentially the same as this node, or it could be different. It could be designed just to store data for memory. I will show you an example of that later on. In this case, they look kind of similar, basically. You have a compute node, maybe another compute node that has memory, and then you share memory. You put some of the memory that you don't access to this remote memory, and when you need to access it, you bring it to your local memory. Basically, the benefit of doing so is to enable even higher memory capacity, because you're limited by how much memory capacity you can have in a single node due to the pin limitations that we discussed, right? With a given chip, you can have only some number of pins. You can extend that with having more channels, for example, and in each channel you can have many ranks, for example. But in the end, you push the limits of power and physical limits and cost limits in a single compute node. So you may need to actually go to the go over the network to some other node to have some more memory. And this is what's real in modern systems, actually. In modern data centers, for example, when you have lots of data and you need to access lots of data, you have these memory nodes. So let me give you an example so that you don't think that memory is something that's just local to your machine. This is a system. This is from a paper that was written about 11 years ago, as you can see. You can see that this is a system with memory blades. You have some compute blades and you have some memory blades, and they're connected to each other via some network. They call the backplane over here, hopefully a low latency network. And this is what you can see in the memory blades. This is what we have been looking at, basically. You have CPUs and you have some memory modules. And if you want to have even more memory, you essentially can attach a memory blade, which is designed purely for memory access. You can see that there are lots of memory. There's lots of memory over here so that you can extend the capacity. And you have some memory controllers and engines or simple processors to enable access to this memory, essentially. Okay, so this is very interesting. Clearly, this is needed to support very high memory capacities. You could do this similarly to storage as well, but we'll not go into that. But you can see that there's local memory in the CPU, and then there's remote memory that the CPU can access in this memory blade. And there could be another memory blade that's far away. So memory hierarchy can extend further and further, where the same trade-off that we discussed, that required us to go to a hierarchy exists. Basically, it's the latency capacity trade-off, right? As you go farther from the processor, the latency increases. As you go farther, the capacity also increases. And that's the purpose of the memory hierarchy in this particular, well, in general. Okay, so there are a lot of interesting work that's going on. This is one work that we've done. If you're interested in this, there's a lot of research that needs to be done in this area also. Okay, so that was to push your limits, if you will, limits of thinking, critical thinking. Now you can think critically and say, okay, how much memory we can have in our servers going into the future? How much of it is wasted? There are a lot of interesting questions over here. But now let's go back to our toy cache example, because I want to cover some of the basic design decisions before we move further to more complex ones. So this was, remember our toy cache example, we actually built a toy cache that was direct mapped. And you know what direct mapped is. Just to remind you, a given main memory block can be placed in only one possible location in the cache. And this was our representation of the direct map cache. And then we showed that this direct map cache is not good at handling conflicts, because if two cache blocks happen to map to the same memory location, and if you need both of those cache blocks in an interleaved manner, cache block A, B, A, B, A, B, A, B, that's your access pattern, and they happen to map to the same location in the cache, you cannot house more than one block in that location, in that index, as we've also discussed. As a result, you get a 0% hit rate. And to solve that problem, we made this cache set associative. And remember, this was the idea. Again, I won't go into detail because we covered this a lot. Essentially, you have two locations that a block can map to in a cache. Basically, blocks with the same index can map into two locations. Right? And then we said that, okay, this may not be good when your access pattern is ABCD, 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 and they all map to the same location or same index. Again, you get a 0% cache hit rate. So we increase the associativity to 4-way, making the cache more complex, as you can see. And then in the limits, your associativity is fully associativity, meaning there is no indexing that's going on. You just compare the tag of the address to the tags that are stored in all possible locations in the cache. Clearly, this is the most flexible. This eliminates all of the possible conflict misses because everything, in a sense, everything conflicts with everything else in the cache because there's no, everything maps to any possible location in the cache, right? So this is the most flexible organization, but you can see that the trade-off is that it's expensive. It has many comparators, large muxes, and we've discussed all of this. And this was the last slide that we covered in full. And I made a joke of this graph, saying that this is a perfect industry graph. Whenever industry shows you something, they don't tell you the numbers of the axis, as you can see, right? But the purpose of the graph is not to really read the numbers. It's to show the trend. As you increase the associativity, hit rate increases. But at some point, you get diminishing returns, as you can see, right? Your hit rate is increasing very, very little as you keep increasing associativity, averaged across many, many workloads. For a given workload, this curve may be different, of course, right? So basically, higher associativity is in general good, but at some point, your returns diminish. And also, as we will see today, as you make your caches higher associative, you need to manage the cache in a more complex way, because a block can map to any location in the cache, and many blocks content for those locations in the cache. Let's assume that you have 1 million locations in the cache. When you actually want to bring a block into the cache, you need to decide which other of the 1 million minus 1 blocks you're going to evict from the cache. And that decision is much more complex now, because you have 1 million blocks in the cache. That decision is much easier if you had only 2 blocks that you're considering. You're bringing 1 block into the cache. Which other of these 2 blocks that you're going to evict in a 2-way set associative cache? Right? So basically, some of the decisions become much harder, much more complex as you increase the associativity of your cache. Okay, so this is where we stopped last time. I said we were going to talk about issues in associative caches. But let me give you a framework of what we're going to talk about for some time. And we're going to talk about a lot of other design decisions and caching as well. Basically, when you bring a block and when you access a block, you can think of each block in a set as having a priority. Priority is importance of the cache block, let's say. How important is it to keep the block in the cache? We're going to talk about what does that mean later on. And the key issue in cache management, set associative cache management, is how do you determine and adjust the priorities of the block, essentially? So there are 3 key decisions that you make in a set. And this is actually isolated to a set because the set of blocks that map to that set are managed together. They don't conflict with the other blocks that are in different sets, different indices. And these can be categorized as insertion, promotion, and eviction. What happens when you insert the block into the cache? That's the first one. Meaning when you fill the cache with a given block, a block is coming from memory or some other cache level. What do you do to the priorities? You could change the priorities. For example, the least recently used management policy says that whenever you bring the block into the cache, make it the highest priority, meaning the least likely to be evicted or latest to be evicted into the future at this point in time. That's one management policy. Is that a good policy? We will talk about that in a little bit. So basically, insertion actually discusses, encompasses where to insert the incoming block. It also, you can also decide not to insert the incoming block. There's another management decision you make over here. If there's some information that you may have for some reason that says this block is not going to be reused into the future at all, don't insert the block into the cache. Basically, if this block doesn't have locality, temporal or spatial. The question is, how do you get that information? Of course, modern systems actually have a lot of predictors, hardware predictors. In hardware, you make a prediction as to whether this block is going to be used into the future. How do you make that prediction? That's more advanced. But you can imagine with history, right? We've seen branch predictors. You can actually have similar predictors based on history that try to decide whether to insert the block into the cache or not. And this is fascinating. This exists in these machines. This machine is already doing something like this at that general level. Programmer can actually say, this block is not going to be reused, as far as I know, and can give a hint using a load instruction. These are called non-temporal loads. And that hint can be used by the cache to not insert a block into the L1 level. You can do this actually in Intel processors today, as we're going to discuss actually next time using prefetching. So that's one decision that you make. Promotion is a decision that you make when you access the cache and you get a cache hit. And then the question is, how do you adjust the priorities of this block that you hit on and all of the other blocks that you didn't touch in the same set, right? Do you change the priority of the block? How do you change the priority of the block? It's actually not easy, basically, because that gives you information. That cache hit gives you information. That cache hit may give you information that it may be a reinforcement that you're going to access that block again. That depends on the access pattern. If the access pattern is such that you think that the reinforcement is correct, then maybe you increase the priority of the block that you just accessed, right? That's the idea of the least recently used mechanism. So least recently used management policy says, whenever I hit on this cache block, I'm going to make it the most recently used, and that priority is the highest. Meaning, I expect that block is going to be accessed again and again and again next time. So you increase its priority. Again, that's not necessarily the best way. Another management policy is completely random. Whenever you hit on a cache block, randomly change the priorities. Could be interesting. And it turns out it's not a bad policy on average across many workloads, because in some workloads, locality doesn't exist very well, and you have set thrashing problems, etc. Okay, and the third decision point in a cache is when you are trying to evict or replace a block. Meaning, when you get a cache miss, when you're looking for a block in the cache, and it's not in the cache, that's a cache miss, then you bring the block, and then you have a bunch of blocks in the set. Now, if the set is full, meaning all of the blocks in the set are actually valid, then you need to decide which block to replace from the cache. If the set is not full, if there's some invalid block, meaning there's no data in that block, then the decision is easy, right? You bring the incoming block and make it valid. But if the set is full, you need to replace a valid block, and the question is, which one do you replace? And that's why this is called a replacement policy. Which block do you evict? And once you evict that block, how do you adjust the priorities of all of the other blocks? And so this is really a general framework, and all caches need to make this decision basically. All levels, L1 cache, L2 cache, L3 cache, L4 cache, DRAM, main memory. You need to make these decisions at all levels, essentially. And even they may or may not be completely or well documented, but there are decisions that are made at all of these points when you do something to a cache. Insert, promote, or evict and replace. Does that make sense? So now you clearly see that there's a huge design space over here, guys. How do you decide all of this? Usually there are simple policies that are used, but things are getting more complex today. So let's take a look at one of these policies, eviction replacement policy, but this also has some implications on insertion and promotion. So which block in the set do you replace on a cache miss? As I said, if there's an invalid block, that means there's no data over there, the tag is not valid, put the data incoming block there, right? That's easy. You're not replacing anything in that particular case. Assuming that there is no invalid block, which is hopefully the steady state of your cache, you consult something called the replacement policy. So what could be a replacement policy? It could be random, as we said. You randomly pick, if you have a 4-way set associated cache, for example, you randomly pick one of the ways and say, I'm going to replace that one. Okay, it could be first in, first out. It could be least recently used, as we're going to discuss a little bit more, because this least recently used makes sense from a temporal locality perspective. Remember, we motivated the caches saying that if we're going to reuse the data that we have used recently in the past. And if you touch something at this point, if you brought that in the cache, probably you're going to touch it again. That's the premise or the anticipation of basic cache. But this is not necessarily correct, right? This is a heuristic in the end. There's no guarantee that this will happen. And if this happens, then you're not going to touch any other data, in fact, right? This doesn't make sense to happen indefinitely in the end. But least recently used is a very popular policy. But there are approximations to this also, because this is not easy to implement, as we will discuss. So people, some processors implement not most recently used, or evict the block that's not the most recently used. Because least recently used requires keeping track of an order within the set, right? If you have a set with 4 ways, if you really want to truly check out the least recently used block, you always need to keep track of the order of use of all of the blocks within those 4 ways. And I'm going to ask you a question in the next slide, so you can start thinking about how many different orderings are possible within those 4 ways if you want to actually perfectly keep track of all possible orders and perfectly implement recently used. We're going to see that it's going to be unsustainable with large associativities. So a lot of caches actually implement some approximation of it. And then there's the least frequently used. So do you keep track of frequency in the cache? That's another question, right? These are relatively simple still. Then if you actually incorporate some other metrics into your decision, like cost, what is the cost of a cache miss? And this is important because if you miss in the cache, and if you are going to evict a block, and if it's very costly to refetch because it's coming from very far away, let's say remote memory, this is a lot more expensive than a block that's easy to refetch, that's not coming from remote memory. So different cache blocks have different costs in terms of latency to refetch. And this should be taken into account in the cache management. Now, it becomes hairy in this case because you're not looking at right now, what am I going to access next? That's one dimension. Now we're also looking at how costly is it for me to bring the data into the cache. And this should factor into the decisions, as I will show you later in this lecture also with a simple and beautiful example, hopefully. This should factor into the decisions because, as we discussed, it's not just about the hit rate of the cache, it's also about the latency. So when you're managing the cache, you need to take that into account. And we'll put energy into it also later on. So it's a complex management decision. And we're just talking about a single cache. And then we're going to talk about the hierarchy soon. Okay, so we're going to talk about that. And actually, a lot of modern processors implement some sort of hybrid replacement policy that tries to get the best of both worlds. Remember the hybrid branch predictors that use different algorithms to cater for different types of branches? Hybrid replacement policies also exist to cater for different access patterns or different access patterns for different sets or within the same set also. These are some things we're not going to discuss in detail, but you can imagine these things. And then the question is, of course, what is an optimal replacement policy? People have tried to figure this out. This is very hard to define because there are many metrics, right? What are you looking for in terms of optimal? If it's about hit rate, maximizing the hit rate, there's an optimal that we will define. But it's not just about the hit rate, it's also the cost. So the optimal is very, very difficult to define in this case. Okay, any questions? Okay, let's take a look at a specific case over here, which is the least recently used policy. And it's really a management algorithm. It's not just an eviction algorithm. LRU, least recently used, is really a management algorithm of the cache, which answers questions about insertion, promotion, and eviction. We're going to look at the eviction part of it, but keep that in mind. And the idea here is very simple. The idea is evict the least recently accessed block. It sounds very simple to implement, right? Now, the problem is it's not that simple, at least if you have large, highly associative caches, because you need to do what is just written over there. You need to keep track of access order of blocks. So if you have 4 blocks, you need to keep track of in which order they were accessed in the past. Which one is the most recently accessed, which one is the next most recently accessed, which one is the next most recently accessed, and which one is the least recently accessed. So you can see that there's an ordering. And when you access one of those blocks, that ordering changes, right? You need to promote the block that you're accessing to the most recently used position or most recently accessed position. And you need to change the ordering of everything else that you did not touch. This is what I mean by priority. And with a 4-way set associative cache, it's not bad. But if you go to 8-way, 16-way, 32-way, 64-way, this becomes intractable. Well, intractable is very strong, maybe very hard to implement. Okay, let's start with a 2-way. Let's start with a direct map cache, actually. If you have a direct map cache, and if your management policy is least recently used, how do you implement that? Basically, you evict whatever is in the cache, right? Whenever you bring some block, you evict whatever is in the cache. So you don't need to store any extra metadata for this. So in direct map cache, there is no policy. Policies apply to set associative caches, clearly. There is a policy, actually. You need to decide whether you actually evict whatever is there or not. So there's actually a policy over there also, but it's not really a replacement of whatever exists. Well, it's kind of a replacement still. So there's a policy, but that requires more metadata. Assuming that you don't do that, assuming that whenever you bring a block into the cache, you don't bypass the cache. You need to evict something and you need to make space for this block. You don't need any additional metadata in a direct map cache because that's how it is. But if you have a 2-way set associative cache, now you have 2 blocks in a set, and you're bringing 1 block. So what additional metadata do you need to implement LRU perfect? How many additional bits do you need to keep track of the ordering between these 2 different blocks? Anybody? Minimally. Yes. Exactly. Yeah. 1 bit to distinguish which one is the least recently used, and that if that bit is 1, exactly. Basically, you point to the way that actually is the least recently used or most recently used. Okay, so that's the minimal. Actually, 1 bit. You can actually do it with more bits, of course, but minimal is 1 bit. Okay, now let's make the question a bit harder. If you have a 4-way set associative cache, how many bits do you minimally need to implement LRU perfectly? Anybody? This is a probability question, actually. If you take a probability and statistics class, these are the questions that you answer over there. Thoughts? Yes. 2 total in the set per block. Yes. That is a correct answer, but it's not a correct answer to this question. That's what you would do if you want to, let's say, minimize your headache when you implement hardware. 2 bits per block enables you to specify which order you have per each block, right? But the minimal number is actually, so in a 4-way associative cache, basically you're saying it's 2 times 4, which is 8 bits, right? You need 8 bits. Yes. 5 bits. Okay, how did you get that? Absolutely, yes. So yeah, basically he did the probability calculation. You need 5 bits. Let's see if you can do this relatively easily without destroying the. So maybe somebody needs to help me with this. So can you see this on the web? If you can see it, I'm not going to switch anything. Maybe I'm going to stop share. What do you think? Is that better? Okay, I guess you can see it. So basically, you have 4 different blocks, right? Basically, you need to position these 4 different blocks. This is the 4-way cache. And you can think of this as LRU, and then next LRU, and then next LRU, and then the most recently used. there could be 4 possible things that you can place into the LRU position. Once you have placed it, there are only 3 blocks left in the N LRU position. And once you've placed it, there are 2 blocks in the next LRU position. And once you've placed all of those, there is only 1 block you can place into the MRU position. And basically, the number of orderings you have is the multiplication of these, because there are so many possible ways you can place those blocks. So it's 4 factorial. And 4 factorial, how many bits do you need to represent 4 factorial? Essentially, that's log 2 to the 4 factorial, which is 5. Log 2 to the 24, right? So that's good. Now, if you do this exercise for n-way associative, you get n factorial, right? And then the number of bits is log 2 to the n factorial. And this is actually pretty bad if n is large. So if n is 8, it's already bad. But if n is not 8, if n is 64, that's 64 factorial. How many people can give that value? What's log to the 64 factorial? I don't know off the top of my head, frankly, but you can put it in a calculator and you'll see that that's a huge value. And this is basically an encoding, right? You have 24 different orderings you can have in this block. And then you need to encode this. So basically, you need to have some, let's call this ordering. And you have 5 bits over here. And then you need to feed this to a decoder to figure out which one is the least recently used, which ordering you are actually, which way is the most recently used, which way is the least recently used, etc. So there's actually hardware complexity, the hardware decoder that determines which order do you have. So I think the answer with 2 bits is actually a bit easier to implement, because what you do over there is you attach, let's say, I'll do a patchy thing over here. You attach 2 bits to each block in the tag store, of course. And you don't need to do that decoding. And these 2 bits basically say, let's say 0, 0 is the least recently used. 0, 1 is the next least recently used. 1, 0 is the next least recently used. 1, 1 is the most recently used. In this case, you don't need to do any decoding, right? You basically have 8 bits, which is not the minimal, which is not, that's why it's not the answer to the question. The minimal is 5. But in this case, you don't need to do any decoding to figure out. You already know if the tag bits for the replacement policy say 0, 0, that way is the least recently. Right? You just need to look for that. Okay? So this is a trade-off in terms of, you always have a trade-off between latency and capacity. And this is another example of it. The capacity of storing the replacement policy bits is low in this case, but the latency of figuring out what you should really evict is longer because you need to go through that decoder. Here, the capacity of storing the replacement policy bits is larger. It's not the minimal, but the latency of figuring out what you should evict is actually much easier because it's already decoded, as you can see. Okay, so hopefully this gives you an example of why LRU is difficult to implement if your caches are highly associative. So we've answered a lot of the questions on this slide now. Okay, and things are presented online as well. It's good. Okay, so I think we've already answered all of these questions. Yeah, we kind of also touched into the logic that's needed to determine the LRU victim, which is the least recently used. Victim is the block that you're going to evict, basically. There's this terminology that has been used. And if you repeat this for n-way set associative cache, you get the number n factorial orderings, and you need to, the minimal number of bits that you need to represent n factorial is log 2 to the n factorial. So this is why LRU is not scalable. That's why most modern processors do not implement true LRU, also called perfect LRU in highly associative caches, because in some processors, we have 128-way associative caches, for example. 64 is very common, 128 is less common, but it exists. Actually, there are 2 reasons why processors don't implement perfect LRU or keep track of the perfect ordering. One is true LRU is complex. We've just discussed this. The second is LRU is already an approximation. It's already a heuristic anyways. It's not perfect, clearly. It's not the best possible cache management policy, essentially. And people have shown that there are other cache management policies that are better, as we will see soon in some cases. So what do processors implement today? At least for the LRU part, because they actually can be using different policies for different types of blocks, if you will. But not MRU, for example, not most recently used, and is an approximation to LRU, right? It basically says, don't evict the most recently used blocks. Among everything else, pick randomly. That's one implementation of not MRU type of policy. So at least you protect the most recently used block in that case, right? There's a hierarchical LRU. Basically, you divide this set into hierarchical pieces, and you try to approximate LRU, or you do perfect LRU at some level, but then you don't do perfect LRU at higher levels of the tree in the hierarchy. Again, I don't want to go into the details of this because details actually vary significantly. I just want to give you the basic ideas of how you can approximate. And then there's also something called next victim replacement. And this is trying to keep track of, basically protect two things, let's say. Maybe you're trying to protect the most recently used and something else as well. How do you determine that something else? It depends on the policy. So most processors essentially don't implement LRU for these two reasons. Okay. Now let's go and look at another question, which I kind of foreshadowed earlier. You have LRU, which you can call principled, let's say, right? Because it is based on some principle, some anticipation that whatever you're going to access right now is going to be accessed next. But then there's another, let's say, principled approach, which is random. You randomly pick to something to evict. Right? You can say maybe the random is not principled, it's just random, right? But random could be principled depending on the access pattern. So which one's better? So let's take a look at an example. We have a 4-way associative cache again, and we have cyclic references to A, B, C, D, E. I think this is correct. If this is what you have, is with LRU, you get 0% hit rate. Right? This is called set trashing. You're trashing a single set, basically. You can only have house 4 different blocks inside that set, but you're really accessing 5 different things in the worst possible access pattern for LRU. A, B, C, D, E, A, B, C, D, A, B, C, D, E. Right? So whenever you're accessing something, you're evicting the thing that you're going to access later. So you get a 0% hit rate. You can convince yourself with this. Yeah, basically the program working set in a set is larger than the set associativity. That's the definition of set trashing. In this case, random replacement policy is a much better approach and a much more principled approach. You randomly pick which one you evict, and hopefully you're not going to evict something that you're going to touch in the cache. Right? And the probability of that is actually relatively low. That gets lower and lower as associativity increases. Okay? And you can do the calculations if you want to get the hit rate, but it's going to be much better than 0%, let's say. Does that make sense? Okay, so this is why random replacements actually make sense. When you have trashing that occurs, you can actually detect the situation with simple mechanisms, right? You can actually detect whether you're getting a 0% hit rate, and you can switch to random replacement policy. That's one of the things that we have evaluated many times, and we've shown that that's a better idea than just keeping on having 0% hit rate. Okay, so in practice, performance of replacement policy very much depends on the access pattern. And I just gave you an example. If your access pattern is this is the worst case access pattern for LRU. It's much better for random. Yeah. And the average hit rate, it turns out, if you average across many, many workloads, average hit rate of LRU and random are similar. This also shows that set trashing happens a lot in real workloads. Of course, it depends on your associativity, but with associativities like 8, 16, 32, it happens a lot. Okay, so best of both worlds is basically having hybrid replacement policies. LRU is good for some access patterns. Random is good for access patterns that are not trashing the cache. And how do you actually put them together? Essentially, you keep track of which policy is doing better by sampling some sets and sampling what would be your hit rate if you actually implemented that policy. You could do that actually in hardware with very low cost. I'm not going to get into the details. And then you follow that particular policy in the remaining part of the cache. You could do this at different granularities, at different parts of the cache, but you could also follow a single policy globally based on the sampling that you do in some sense. Okay? But you could also follow a different policy locally at different indices based on the sampling you do in every set. Okay? Of course, the latter one, the local policy per set is much more expensive in terms of hardware because you need to sample actually a lot more in that case, but it's possible. So I find this fascinating, actually. And there are many implementations of set sampling that happened, especially in recent years. But if you're interested, you can take a look at this paper, which I'm going to talk about at some point to talk about something else, actually, not this. Okay, any questions? Okay, let's talk about the optimal replacement policy, because this is an interesting question in general. And this was well defined for miss rate, if you will. There is this thing called Bellidy's OPT policy. And the idea is to replace the block that is going to be referenced furthest into the future by the program. That sounds great, right? The question is, how do you actually know this? Knowing this is the problem. This is not implementable. People have actually tried to approximate this using some access by tracking access patterns. There's some work in this direction. But this was first proposed a long time ago for virtual memory systems. So how do you implement this? Basically, it's unimplementable. How do you even simulate this? When you're actually simulating a program is actually not that easy to know about also. But if you want to do some interesting project, this is something you can think about. So, okay, is this optimal for minimizing miss rate? Under some assumptions, yes. I'm not going to go into the proof of it. You can read papers about it. Now, the interesting question is not this, though, because miss rate is only part of the equation, right? We also talk about miss latency, which is execution time, right? What we really care about is not the miss rate of a particular cache or even the cache hierarchy. It's really how long do I take to execute this program if I'm concerned about performance, right? It's not the miss rate of a particular cache. Those may be interesting to examine if you're having problems locally, but in the end, the bottom line is how long does it take for me to execute this program? And if this is the question, then the answer to this question is this is not optimal for sure, because it doesn't take into account the cost of a cache miss, the latency of a cache miss, basically. Not all cache misses are equal, and I will show you some examples of this, but I've already given you an example, right? If you can fetch the block quickly after you evict it, assuming you need it again, that is a not so costly cache miss. If you cannot do that, if you need to wait for, let's say, I don't know, seconds to fetch the block because it's coming from some remote memory for whatever reason, then it's a much more costly cache miss. And if your replacement policy does not take this into account, it may evict the block that's costly to refetch, and as a result, it may actually destroy your execution time. Okay. Yeah. So basically, this is one reason where the miss is serviced from, local or remote, which cache hierarchy level. And then we're going to see an example of miss overlapping, which is an interesting thing, which is going to segue us to the next lecture as well. Okay, and then I'm going to talk about this paper because this paper actually introduced some of these ideas. Okay, so I'm going to get back to this. But let's talk about some of the other design decisions. Right now, we've covered some things and we went a little bit deeper, but let's pull back and talk about some other design decisions that we have. So we've talked about the tag store, right? We have a val bit in the tag store. We have a tag. This was the basic cache. Now, if you have a set associative cache, we added the replacement policy bits that we just discussed. But there are other things that you can add. This is the dirty bit or the modified bit. Essentially, do you keep track of whether or not a block is modified in the cache? Now, this goes to another design decision, which is, is your cache write back or write through? Meaning, whenever you do a write to your cache, do the write propagate immediately to the next level, or you keep the modified data in the cache and you propagate the writes, or you propagate the updated value to the next level after it's evicted, after the block is evicted. And this is a very fundamental design decision. I'm going to talk about handling writes in the next few, let's say, minutes. The key question is, when do we write the modified data in a cache to the next level? Write through means at the time the write happens, all caches or the next level gets updated. Right? Write back means when the block is evicted. So this classifies caches into two different categories. You can have write back cache and write through cache, and they have clearly different trade-offs. Write back cache, you can combine multiple writes to the same block before eviction. So these are called write combining. This is called write combining. Basically, you have a block and you keep writing to this block, right? Either to the same bytes or different bytes, it doesn't matter. You keep writing to it. And if you actually don't write to the next level, what you're doing is you're combining all of those writes in the same block in this particular level of the cache, and you write back all of those combined writes into the next level when the block is evicted. Right? That's the advantage of a write-back cache, right combining, if you will. This potentially saves bandwidth between cache levels and saves energy. If you propagate every single write to the next level, you're basically wasting bandwidth, right? Because there's some bus between the caches, and you're basically keeping that busy. That bus may be used for something else, and clearly you're wasting energy potentially. So of course, the downside of the write-back cache is additional complexity, right? You need to have this extra bit in the tag store indicating that the block is modified or dirty. These are two terms that are used actually in caches. And we will see it in virtual memory also in the next lectures. So this is the trade-off. Write-through cache is simpler design because you don't need to keep track of this, let's say, dirtiness. And also you don't need to write back when is needed. But of course, I'm going to talk about this positive later on. But of course, it's more bandwidth intensive and there's no combining of writes. There's another benefit of a write-through cache, which will become a little bit more clear when we talk about cache coherence very briefly in this lecture. How many people know about cache coherence? Okay, some people. How many people do not know about cache coherence? Okay, that's what I would expect. More people would raise their hands. So we're going to talk about cache coherence. Cache coherence is an issue that happens when you have multiple processors, and each of them have their own private caches. Hopefully, at the end of this lecture, we'll get to it, or maybe early in the next lecture. And when one cache writes to a cache block, that is also a cache that one processor writes to a cache block that's cached locally, and another processor needs to has the same cache block cached. What happens, right? You have some inconsistency in the values because you've written to this local cache, but the other cache is not updated. So this is the cache consistency or cache coherence problem. Now, if you do write through, this problem is a lot easier to handle because whenever you do a write, all of the other caches are updated essentially, and you don't have the cache coherence problem as bad, if you will. If you do write back, unfortunately, this problem gets amplified because the writes that you do locally as a processor don't get seen by some other processor to the same cache block. So write-through caches are actually simplifying the cache coherence design, but they have other downsides, as you can see, right? Bandwidth intensive, etc. As a result, a lot of the caches today are write-back. There are some cases where you have write-through, but write-through is not very common today, especially due to the importance of bandwidth as well as energy. Write-through is being avoided most of the time. So today, you should also consider energy in the design decisions a lot. That was not the case, let's say, 20, 30 years ago. Okay, so let's talk about writes a little bit more. Writes actually add a lot of other interesting things. Do we allocate a cache block on a write miss? So basically, you do a write to a cache. For a first level cache, this could be a store. And you miss in the cache. You bring the block from memory. Do you allocate it in the cache or do you not allocate it? Meaning, do you evict something else from the cache? Now, this is actually a general design decision, but with writes, it becomes a little bit specialized because writes may be considered a bit more special than reads, right? Because writes are not on the, you can tolerate the latency of writes more easily because whenever you do a read, there should be some dependent instructions probably, right? With writes, you usually don't have dependent instructions following them because you're writing to some value in memory. Maybe you're going to touch that many number of cycles later, but not soon, hopefully. So basically, there are two design decisions that you make over here. You allocate on write miss or not allocate. Now, if you allocate on a write miss, what may happen is you write the cache block into the cache, and then you may have many updates to that cache block. Right? So if that happens, this is good. You can combine the writes basically instead of writing individually to the next level, right? If you allocate. So that's the upside, right? Combining again, very similar to the previous one. And this is also simpler because write misses can be treated the same way as read misses, assuming that you're also allocating a block into the cache whenever you miss on a read request, like a load request, as opposed to a store. Okay, the downside is it requires a transfer of the whole cache block to the cache if you actually want to allocate on a write miss. Now, no allocate essentially is opposite. Basically, you can do the opposite of these things. But it also has one advantage, which is it conserves cache space if the locality of written blocks is low. So it can actually give you a potentially better cache hit rate. Of course, the downside is it's not able to combine, right? So it really depends on what kind of access pattern you're seeing to the cache. And that's really the key that I want to get over here, that I want you guys to understand. The access pattern is the most important thing into the cache. If the access pattern is such that you don't need write combining, but you actually need to conserve cache space and the locality of writes is low, then no allocate on writes is actually a better design decision. And again, you can have hybrid policies over here. This is easier to implement in the sense that you basically need to decide whether you actually put the cache block into the cache or not put the cache block into the cache or not even fetch the cache block to begin with. You just need a predictor to decide which access pattern you're seeing. And this is I said this is easier than let's say what we discussed, hybrid replacement policies, if you want to have a hybrid policy over here, but it requires you to detect the access pattern, which may not be that easy. So a lot of the current processors try to use heuristics to detect the access patterns and try to decide what to cache and what not to cache and make some of these decisions. More recently, people are looking at the machine learning techniques to actually discover or predict these things in a much better way and with limited success. So let's see. Okay, let me give you one more thing about the writes. This is actually trying to handle the write combining issue. So assume there's an access pattern where the processor writes to an entire block over a small amount of time, like streaming through the block. And the idea is basically you have a 64-byte block. Let's assume that you write to every single byte. The first 8 bytes, the next 8 bytes, the next 8 bytes. So you do it for every 8 bytes. So 8 bytes you write. Then the question is there any need to bring the block from the cache to from the memory in the first place? You've completely overwritten the block. You didn't read anything out of there. If that's your access pattern, there's no need to bring the cache block, right? You can just create the cache block inside the cache and then write it to memory. Does that make sense? Of course, this doesn't work well if your write granularity is smaller than your cache block granularity. Today, as we discussed, the cache block granularity is 64 bytes. Write granularity store word, as you've seen, is 4 bytes, right? Or 8 bytes, let's say. You can have 8-byte stores also. That's much smaller than the cache block granularity. So how do you implement this? So basically, the idea is sub-blocking. Simply write to only a portion of the block called a sub-block. For example, 4 bytes out of 64 bytes, right? Now, the problem is what I just said, the granularity mismatch. You have valid and dirty bits associated with the entire 64 bytes. And if you write only 4 bytes, and if you don't have the remaining part of the block, you have a problem, right? So what do we do? Well, sub-blocking. Replicate the valid and dirty bits with the sub-blocks. So associate valid and dirty bits with sub-blocks. Or the general idea is divide a block into sub-blocks. This is also called sectors. And have separate valid and dirty bits for each sub-block or sector, and allocate only a sub-block or a set of sub-blocks on a request. So whenever you do a write to a sub-block, you basically set the valid bits, set the dirty bits, write the data, and of course set the tag over here, and all of the other valid and dirty bits are 0. So this way, you don't need to bring the cache block into the cache, right? Because you're just writing to a sub-block, and that sub-block is not going to, you just modified it, right? You don't need the old data that was there. Okay, hopefully that makes sense. So the huge benefit of this is no need to transfer the entire cache block into the cache. You can just write to a sub-block, and then you can write back the sub-block, modified sub-block later on, and then merge the data. So that's good. A write simply validates and updates the sub-block, basically. Now, there's also another benefit, because now you have more freedom in transferring sub-blocks into the cache. A cache block does not need to be in the cache fully. We kind of reduce the granularity of management. The granularity of management was 64 bytes. Now we actually are doing 4 bytes at a time because that's our sub-block granularity. And whenever you fetch something, you just fetch whatever 4 bytes you may need, or whatever, let's say, which pattern of 4 bytes that you want, let's say, assuming you know that, assuming you can predict that. So this gives you a lot of flexibility right now. Now, the granularity is interesting because the block is still at the granularity of 64 bytes, right? So we did not change the size of the tag. That's the benefit of sub-blocking. You just increase the valid and dirty bits, but you do not have, this is the difference from having smaller blocks. So the question may be that, okay, instead of having 64-byte blocks, why don't we have 4-byte blocks, right? If you have 4-byte blocks, your tag size increases a lot more. Here, we kept the tag size the same, but made sub-blocks. Yes, we paid the penalty of additional valid and dirty bits for each sub-block, but the tag size did not increase, okay? Okay, so basically, this gives you more flexibility in management because you can decide how many subblocks and which subblocks do you transfer on a read as well, on a read request, as well as a write request, clearly. Of course, the downside is more complex design. You have more valid and dirty bits. And clearly, based on the design decisions that you have, you may not exploit spatial locality fully. But the good thing, if you have a streaming write access pattern, if you start from the beginning of the cache block and write 4 bytes to the beginning, 4 bytes to the next one, 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 you populate the entire block inside the cache, and you don't need to read anything from memory or the next level. So with streaming writes, this sort of design shines. But it also has a lot of other flexibility, as I discussed, that can enable much better cache management. So a lot of caches are actually sub-blocked today. Okay, let me give you one more design decision, and we'll take a break. So there are a lot of other design decisions, instruction versus data caches, for example. Do you keep them separate or unified? Do you have both instruction and data in the cache at the same time? Well, if you have them unified, let's take a look at their pros and cons. The big pro is you dynamically share the cache space between two different types of, let's say, data, instructions and data. You get better overall cache utilization, meaning there's no over provisioning that might happen if you actually partition the cache into instruction versus data. Right? So we'll talk about that later on, actually. But if you partition the cache to have separate instruction and data, let's say you have 64 kilobyte instruction cache, 64 kilobyte data cache. If your instruction working set is only 1 kilobyte, you're wasting 63 kilobytes of the 64 kilobyte instruction cache. If your data working set is 127 kilobytes, you're thrashing your 64 kilobyte data cache, even though you had actually additional 63 kilobytes in the instruction cache that you cannot use because they're reserved for instruction. So a combined cache of 128 kilobytes can actually much better service a 1 kilobyte instruction set plus 127 kilobyte data set, right? Because combined, they're 128 kilobytes. Okay, that's basically the effect of better overall cache utilization. Now, of course, the downside is instruction and data can also evict and thrash each other. I gave you a very good example. What if you have a worse example where the working set together is much larger than the cache space? Now you don't have guaranteed, let's say, space for either instructions or data. As a result, this may actually hurt your pipeline a little bit. Some data can evict the instructions. But again, if you have a unified cache, you can potentially manage it. But the real reason why at least the L1 caches are separated between instruction and data in modern processors is this. And it's dictated by the pipeline, as we have discussed in the last lecture. Instructions and data are accessed in different places in the pipeline, right? Remember, we formed the pipeline processor. You fetch the instructions in the beginning of the pipeline, and then you do stuff in the pipeline. And then you need to fetch the data for some instructions. So these two things happen far away in the pipeline. So that makes actually a lot of sense to have separate instruction and data cache so that you can have fast access integrated into the pipeline stage where you actually need to fetch the data. And this is the main reason why instructions and data caches are separate in modern processors. So basically, because of this reason, first level caches are almost always separated because of the pipeline constraints, but outer level caches are almost always unified. So L2 cache, there's no distinction between, there's no separation between instruction and data. In your management policy, you can actually take into account instruction versus data, but that's a different question. Okay, so let me cover this also, and then, okay, and then we'll take a break. Actually, I take it back. This is a good place to take a break because I have a lot of things to cover in the multi-level cache design and management. So let's take a break until 15:20, and then we're going to come back and talk a lot about multi-level cache management afterwards. Okay, this is where we stopped. I mean, I give you a lot of design decisions. I'm going to give you more design decisions, as you can see. As you can see, this is a fascinating area, but it also shows you the complexity. Now, let's talk about multi-level caches. Multi-level cache design and management actually makes things more complex because so far we've been talking about the design decision at a single level. At a single cache, you have many, many design decisions, some of which we did not cover. But when you go to multi-levels, you need to manage the hierarchy holistically as well. And that introduces a different set of constraints and design decisions that you need to make. And one of the key things that I want to emphasize is the first thing that's written over there. Cache level greatly affects the cache design and management. The policies that you employ are basically dependent on which caches we're talking about, L1, L2, L3, L4, main memory. They're all
dependent on where they are, basically. And we've seen some examples of this, right? In the last lecture, I said, for example, L3 caches have high capacity. Their latency is not as important. As a result, you can play circuit tricks to make the density a lot higher over there and maybe trade off, meaning make the capacity higher at the expense of some more latency because it's long to access the cache anyways. Everything okay? Okay, so let's take a look at another example of this. First level caches, second level caches, and further level caches. We said that first level caches are partitioned to instruction and data because of their level, because they're serving the pipeline, right, immediately. So they're partitioned. And in general, in the first level caches, decisions are very much affected by the cycle time and the pipeline structure itself. Because you need to get the data very quickly into the pipeline, instructions are especially more important, actually, because instructions, if you don't get the instructions in a pipeline manner quickly, you'll stall the entire pipeline, right? Data is also important in the back end. But basically, these are usually smaller, lower associativity, and latency is critical, as we've discussed. A design decision, for example, you have the tag store and the data store. And we said earlier that in our basic cache, tag store and data store, we access them in parallel, right? We index the tag store, we index the data store, we get the tags and data in parallel, we do the tag comparisons. If there's a match, we use the data that we actually accessed concurrently with the tag store. If there's a mismatch, then we discard the data. Now, you can do this in parallel in the first level. And first level is small, and first level hit rates are high. So it makes sense to access the tag store and the data store in parallel. Now let's take a look at the second level. Second level, you're not as bound by the pipeline constraints, so your access latency is less important. It's still important, of course, but your hit rate, you need to balance the hit rate and access latency. So usually these are large and highly associative. Latency, again, is not as important. So one design decision in the tag store and data store is to access them serially. So you have the tag store, you have the data store. Instead of accessing them in parallel, you first access the tag store, and the tag store indicates whether it's a hit or miss. If it's a miss, you don't access the data store. You saved a lot of energy. That's nice, right? And if a cache is highly associative, your data store is expensive to access because you're accessing a lot of things. Or if your cache is large, your data store is expensive to access. Now the downside is if it's a hit, if the tag store indicates a hit, you need to access the data store after that. So there's some additional latency. But that access may be easier to do also because when you get a hit in the tag store can also tell you which way of the data store you just need to access, right? You access only that way and not the remaining n ways or n-1 ways where n is your associativity. So basically, if you do serial access to the tag store, you determine whether it's a hit or miss and which way you hit on first, you save a lot of energy regardless at the expense of some latency, of course. So that's the trade-off you're making at the second level. And second level, tag store and data store can be accessed serially, and depending on the design decisions and how big your second level is, in modern processors, they're accessed serially. But now if you go to the next outer levels, where your cache is, let's say, 48 megabytes, 64 megabytes, even larger potentially, access energy becomes an even larger problem due to the size of the cache. And tag store and access data store are usually accessed serially to save energy in that case. And access latency is less of a problem at that point because you already waited so long. Maybe you can wait another 5 cycles, right, from the processor's perspective. So that's the trade-off, basically. Outer levels are very different from the inner levels. Inner levels are closer to the processor. Everything is dictated by latency and access time, whereas outer levels, less so. Another thing in the outer levels is the hit rates of outer levels are actually lower than hit rates of the inner levels on average, again. As a result, it usually doesn't make sense to access the data store in parallel with the tag store because many of the accesses you're going to miss anyway in the cache. So you should really avoid those large data store accesses. And data store is really the large part of a cache. Okay, so that gives you another example. Another design decision. Hopefully that's clear. Any questions? Okay, another design decision is serial versus parallel access of cache levels. So parallel means that you access the next level in parallel with the previous level. So whenever you start the access of the previous level, you also start the access to the next level. This is a form of speculative access, right? It basically is useful if you miss in the first level, of course, in the previous level. So this gives you faster access to data. If previous level misses, hopefully the next level hits. But of course, you can generalize it to n levels hierarchically, right? Now, the downside is if the first level hits, if the previous level hits, you have unnecessarily access to the next level. You should stop that access or ignore the data that comes out of the next level, right? So this is a trade-off, basically. It's a latency energy trade-off again. But unnecessary accesses waste energy, but they also waste bandwidth from the cache. So they're not necessarily good. But if you do the accesses serially, meaning next level is accessed only if previous level misses, you have slower access to data if previous level misses, clearly, because you start the next level's access only after you figure out that it's a miss in the previous level. But the upside is you have no wasted access to the next level if previous level is a hit. So the serial access, actually, usually people employ serial access. We're going to talk about when you may employ parallel access, hopefully tomorrow a little bit. But usually in the cache hierarchy, you employ serial access unless you have good reason to believe that you may miss in the cache, for example. If you do serial access, next level does not see the same access as the previous level, right? So this actually adds another dimension to the management. Now, the first level cache sees all of the accesses coming from the processor. Next level doesn't see all of the accesses because you don't expose those accesses. Only the missing accesses from the first level are seen by the next level. The next level, only the missing accesses from the second level are seen by the next level. Basically, fewer and fewer accesses are seen by later levels. Now, this has implications. Essentially, a previous level is acting as a filter. It filters some temporal and spatial locality. So the different locality that's seen in the access pattern is very different across different levels in the end, which means that management policies should be different across different levels, and they are different. This is one of the other reasons why cache management policies differ across these different cache levels. Okay, so I'm going to talk about a little bit more, but just to put this into perspective, there are clearly L1 and L2 caches over here, but these folks have decided there's a system level cache that's shared by the GPU, CPU, and accelerators also. So clearly there are other decisions that you make at the other outer levels of the cache hierarchy, right? If you look at L1 and L2 caches, they're relatively tightly coupled to the cores over here. But once you go to the outer level, you also go out to the system. Right? Once you're out at the system, you actually have other stuff that may be sharing data across each other. As a result, you may actually want to have caches that are shared across different types of processors as well. So it's important to keep that in mind, actually. Essentially, once you go outer and outer, you're far away from the processor and you're out in the system, and there's other stuff that you need to consider, if you will. Okay, so this is just to give you some examples that we've seen earlier. And also, it also shows that how big these things that we're talking about is. So this is the reason why L3 caches are not accessed in parallel in terms of tag store and data store. You access the tag store first and data store next, because this is a huge cache, as you can see, right? You don't activate a huge amount of your chip just to get data that you're going to miss on anyway, that you're not going to need anyway. Okay, so and this is true everywhere. Okay, let me give you some other things. I'm not going to talk about this in detail, but I decided that we would use some real examples. So in some cases, the programmer can decide to bypass caches. I mentioned some prefetch instructions or non-temporal load instructions earlier, but in this particular case, in an NVIDIA GPU, A100, for example, you can bring data from L2 cache directly to the scratchpad. You basically bypass L1 and register file, which used to be there in the past. So you can use some instructions that directly bring data from L2 to scratchpad. So basically, the programmer actually can have some control over the caches or the scratchpads, depending on what instructions are exposed. So if somebody asks you a question, are caches part of the microarchitecture or the ISA? Then the answer is probably it depends, right? It depends on whether the programmer can manage the cache or not. Okay, so I'll give you another example. In later NVIDIA incarnations, H100, for example, you could actually take the data directly from the global memory to the shared memory, which is essentially the scratchpad in NVIDIA terminology, bypassing the L2 caches. So you don't need to bring the data into the L2 cache. Again, this is under programmer control. You can also move the data from a scratchpad of one multiprocessor to another multiprocessor, again, under program control. So basically, there are a lot of other design decisions that we're not going to tackle. And this is an example, right? What do you expose to the programmer, right? If you expose more, will the programmer do more? If the programmer is an expert, perhaps, but maybe not all programmers. And you can see the relative sizes over here, right? The L2 cache 60 megabytes, and this is 80 gigabytes, and shared memory, I think we had the number earlier. Okay, so let me give you at a high level, what are the other design decisions, some of the things that we're not going to cover. Which levels do you place the block into? Whenever you fetch the block from memory, for example, which levels do you place the block into? L1, L2, L3, all of them, a subset of them? This is a good question, basically. Modern processors can use predictors, for example, for that, but this could be done under programmer control as well. Which levels do you evict the block to? If you're evicting from an inner level, which outer levels do you put it to? Do you put it directly into L2? Well, depends. Maybe are you going to reuse it soon? Again, if you can predict that reuse patterns, maybe you don't put it anywhere. Right? You basically say, I think I'm done with this block. I'm not going to touch it for a long time, so I'm going to drop it. It's not modified, for example. It's not dirty, meaning I can drop it, right? I don't need to do anything with that because the copy is already up to date in memory or somewhere. Okay, so bypassing versus non-bypassing of levels actually is important. Essentially, that's what we're talking about. Which levels do you bypass? Which levels do you not bypass? There's a huge design space over here. And then there's the other design decision, which is called inclusion in memory hierarchies. Your memory hierarchy can be inclusive, exclusive, or neither. This is called non-inclusive. And there are all kinds of processors that implement these different types. Inclusive means a block in an inner level is always included also in an outer level. So basically, L1 is included. The contents of L1 is included in L2. The contents of L2 is included in L3. Essentially, these are inclusive. And this simplifies cache coherence, actually, which we're not going to go into. Exclusive means that a block in an inner level does not exist in an outer level. So this is strictly exclusive. So inclusive, the downside of inclusive is you have data duplication, right? L1 has some data. L2 also has the same data. L3 also has the same data in L2. So you have a lot of data duplicated across the hierarchy. You're not really utilizing the cache space very efficiently. If you say exclusive, whatever I'm going to have in an inner block is not going to be replicated anywhere else, or basically a block can be present only at one level. Then you're actually using the entire cache space in a much better way. But it turns out inclusive is easier to implement coherence, whereas exclusive is a bit harder to implement coherence, because if you do inclusion, you just need to check the later level caches or some level caches for coherence. Okay, and then there's a non-inclusive, which says basically, I'm not going to enforce either of these. A block may be replicated at some level, or it may not be replicated. I don't keep track of this. I don't enforce it. My coherence protocol is not going to depend on it. So it's going to happen. So this gives you design freedom. Let's say this relaxes the design decisions. In exclusive hierarchy, you need to ensure that no other cache has it. In an inclusive hierarchy, you need to ensure that every other outer cache has it. In a non-inclusive hierarchy, you don't need to care. You can basically bring some data and some other cache may also have it, fine. As long as you keep it coherent and consistent, no problem, right? So, okay, there's more to talk about in this design decision also, but I gave you the basics, hopefully. But now you can see other dimensions also, right, when you go to multiple levels. Okay, so let's talk a little bit about cache performance. We've kind of been implicitly talking about this, but I want to cover a couple of things that are important. So there are a bunch of cache parameters that we've discussed. Even the management policies, if you actually add the multi-level management policies, you can add them over here. But cache size, block size, associativity, the management policy within a single level, as well as management policies across levels. All of these affect performance. We're going to not look at performance. We're going to look at hit-miss rate because it's easier to reason about. Let's take a look at the effect of cache size on cache hit rate, as you can see in this industry type of graph. Again, no numbers. So basically, cache size is measured as total data capacity. Usually when we refer to a 60 megabyte cache, you don't include the tag store. You always talk about the data store. Tag store is some extra Could be kilobytes or megabytes, whatever, on top of that. But basically, if you have a bigger cache, larger cache, you can exploit temporal locality better. And this kind of shows that, right? As cache size increases, your hit rate increases, and you get diminishing returns at some point. Again, averaged across many workloads. Different workloads will behave differently, as I will show you soon. If you make the cache too large, clearly this affects the hit and miss latency adversely. Bigger is slower. We know that very well by now. If you make the cache too small, it does not exploit temporal locality very well. Useful data is replaced often, basically. So there's this notion of working set, where the entire set of data the executing application references, within a time interval, of course, may be present in the cache. So where your hit rate saturates is when your working set fits in the cache. So if your cache size is a little bit larger or equal to your working set size, you don't expect your hit rate to increase further by increasing the size of your cache, essentially. Hopefully this makes sense. Of course, working set of a program it has a temporal component of it as well, right? At a given point, you're working on some data, as we will see later on, actually. We're going to take advantage of that also. You would like to keep the working set in your cache as much as possible, essentially. Okay, so benefits of larger cache actually widely varies. It depends on the size of the working sets, for example. I'll give you some examples over here. So this is real data measured in some paper, as you can see over here. This is the number of ways from a 16-way 1 megabyte L2 cache. So if you actually use only one way for this application, the hit rate, or misses per one, this is the miss rate, misses per 1,000 instructions, the miss rate is the same as, almost the same as, when you use 16 of the ways for that application. Basically, if you increase this, in other words, if you increase your cache capacity by 16 times, it doesn't matter. For this application, the miss rate doesn't change. Why? Because of the access pattern, it's not benefiting from a larger cache, at least within that range. Right? So this is an application where the utility of the cache is low. Another application, you're increasing the cache size from 1 divided by 16 megabytes to 1 megabyte. 16x, and you see that there's a huge decrease in the cache miss rate. So this is an application that benefits a lot. And another application, you can see that after you increase the cache size by about 5x or 6x, you don't get any benefit because your miss rate is almost zero. Right? Basically here, this is an example where your application fits in the cache and larger cache doesn't benefit the application. This is a saturating utility. Application has saturating utility from larger caches. So you see all kinds of behavior like this. These are the three major patterns of behavior that you would have in larger caches. But again, it's very application dependent. It's very access pattern dependent. Okay, so let's talk about block size. We talked about associativity earlier. I'm going to talk about the slide again, but I'm not going to go into that in detail. But block size is also important. Block size is the data that's associated with an address tag, as we know. Now, this is the curve that you get as you increase the block size, assuming you keep the size of the cache constant, data set size, because you have to keep something constant, right? So if you have two small blocks, I should also mention that block size is not necessarily the unit of transfer between the hierarchies. If you do sub-blocking, for example, you transfer sub-blocks between the different levels, etc. So I'm ignoring sub-blocking, etc. in this graph. We're just looking at blocks, no sectoring, no sub-blocking. So if you have two small blocks, each block doesn't exploit spatial locality well because the block is smaller, 8 bytes, for example, or 1 byte, let's say. And you have larger tag overhead, clearly, right? So basically, that's why your hit rate is low. And as you increase the size of the blocks more and more, you exploit spatial locality better. And you reduce the number of blocks you have, of course, in the cache, assuming your cache size is constant. So at some point, your performance starts reducing because the number of blocks you have is small, becomes smaller. So if you have two large blocks, which is at the other end of this curve, you have too few total blocks. As a result, you do not exploit temporal locality well. So assuming your cache size is constant, larger blocks exploit spatial locality as you increase the block size, but you reduce the number of blocks you have in the cache as you increase the block size. As a result, now you stop exploiting temporal locality really well, because in the limits, you have a large cache, 1 megabyte cache and 1 megabyte block. That's a single block. You'd better have extremely good spatial locality there, right, to exploit that. And also, we'll talk about some other issue with large blocks soon. Basically, large blocks waste cache space and bandwidth and energy if spatial locality is not high. And also you need to bring the large block to the cache, right? If you have 1 megabyte block, it takes a long time to bring the 1 megabyte block to the cache, because remember the memory interface we had was 64 bits. Right? You need to fetch that 1 megabyte block 64 bit at a time from memory. Of course, you can widen the interface with techniques that we've discussed, but it's not going to be you fetch all of the 1 megabytes at a single shot. Okay, so large blocks, basically this is, I foreshadowed this point. Large blocks can take a long time to fill or to place into the cache. So what a lot of processors today do is they do a critical word first, assuming you know this information. At the first level, for example, you know the information that, oh, this load requires this word in this block. So you try to fetch that word first from memory and bring that first, as opposed to the entire block. So you prioritize basically what you fetch within the block. So supply the critical data to processor immediately. But large blocks can waste bus bandwidth, and sub-blocking actually solves this problem partially, essentially. Sub-blocking has this advantage, as we have discussed earlier. Essentially, by associating the valid and dirty bits for each sub-block, you just need to bring the sub-block to the cache. If you're reading a location within the sub-block, you just need to bring that sub-block, right? You don't need to bring the entire block into the cache, basically. You can bring the remaining parts of the block lazily, let's say, over time, potentially, if you think they're going to be useful based on some prediction mechanism that you have in the processor. Okay, so we talked about sub-blocking. We know when it's useful, but clearly it can be useful in implementing large blocks without having to always pay the penalty of fetching the large blocks into the cache. Okay, associativity, we've already seen this graph, so I'm going to skip this, but I will handle this question. Maybe someone can answer. So basically, we know that larger associativity has benefits and diminishing returns. Smaller associativity is not good for hit rate, but hit latency is important, so it enables lower latency. But a fun question to answer is, do you need a power of 2 associativity? Anyone? Can we have a, let's say, 5-way associative cache? Or 3-way associative cache? Who says yes? Yes to a 3-way associative cache. Okay, good. Who says no, we cannot have a 3-way associative cache? Okay. Okay. People who say no, let me show you that I can make a 3-way associative cache. This is a 4-way associative cache. Nobody has a problem with this. We constructed it. How do I make it 3-way? Well, I get rid of this, and that's 3-way. And nothing changed. So yes, you can have it. I'm not joking, you can have it, this works, right? But basically, there's no reason to have a power of 2 associativity, because associativity is not about indexing, right? You don't use the address to index into a set. You really do this comparison. So if it's a 3-way associative, it doesn't matter. Whatever matches, you take. As long as this logic is correct, as long as you figure out which one is hitting, you can have a 3-way associative cache. You just don't use the other possibility over here, right? You just don't use one of the inputs of this mux, essentially. Make sense? Okay, so hopefully you'll convince yourself if it doesn't make sense. But this is our 8-way fully associative cache. Well, how do you make it 7-way? Get rid of 1. This is my 7-way. If you want to make it 9-way, well, you need to widen the mux to 16, unfortunately, but you waste, you can add 1 more, essentially, right? Okay, so basically associativity is not dependent on anything in the address being any power of 2 value, basically. Okay, let's talk about classification of cache misses. By the way, I should say that there were caches that were implemented in real processors that were 3-way, because they found out that that was the way to actually fit the blocks into their processor. I think HPPA had some cache that was 3-way, let's say. Okay, let's classify the cache misses. We're going to add coherence miss later on, potentially, if we have time, but the cache misses can be classified into 3 categories. This is important because this determines actually how you can reduce the different categories, or this gives you insight into that. Compulsory miss, capacity miss, conflict miss. Compulsory is, this is the first reference to an address. Whenever I talk about an address, I'm talking about a block address from the perspective of the cache. Always results in a cache miss. This is compulsory. You cannot eliminate it with just caching, right? So subsequent references to the block should hit in the cache unless the block is displayed from the cache for these reasons. Either it's a capacity miss or a conflict miss. So capacity miss, cache is too small to hold all the needed data, basically. It's defined as the misses that will occur in a fully associative cache with optimal replacement. which may be hard to define. Well, for hit rate, it's easy to define. For execution time, it may be hard to define, of the same capacity, essentially. Essentially, defined as the misses that are not compulsory and not conflict misses. You can think of it that way. But basically, this is a valid definition that doesn't incur the conflict miss in it. Defined as the misses that would occur even in a fully associative cache with optimal replacement of the same capacity. Basically, you do whatever you do, you don't have a conflict miss, and you still get a miss that's a capacity miss. And conflict miss can be defined this way. By the way, this is not a circular definition. Conflict miss. This is the definition of how to eliminate conflict misses over here. And then after that, you can define the capacity miss. And conflict miss is basically you cannot classify it as a capacity miss or a compulsory miss. Essentially, you don't have a fully associative cache and you have a miss in the set. Well, you probably have a problem with the conflict over there. If you don't have a fully associative cache, basically, by definition, it's a conflict miss, essentially, if it's not a compulsory miss. Okay, so how do you reduce each miss type? Compulsory, caching only access data doesn't help, basically. Because caching says, I access the data, I'm going to re-access it again, I'm going to cache it. So you need to do something else. Unit can have larger blocks. Larger blocks can actually eliminate compulsory misses that occur with smaller blocks, right? That's possible. But what we're going to discuss tomorrow, prefetching actually helps. The idea is to anticipate what you're going to need next and prefetch into the cache, as opposed to waiting for the processor to access it. Why don't you just anticipate? The processor is accessing blocks in a streaming manner. Address A, A plus 10, A plus 20, A plus 30, A plus 40. Whenever I access A, I say, oh, I should bring A plus 10, A plus 20, A plus 30, A plus 40, A plus 50, all of those blocks into the cache also. That's the idea of prefetching. And we're going to see that. How do you eliminate conflict misses? More associativity helps over here, clearly. But there are other ways to get more associativity without making the cache associative. And there are a bunch of stuff that we're not going to talk about in detail. There's a victim cache, better randomized indexing into cache, better utilizing the cache, and software hints like we have seen earlier. I'm going to talk about some things a little bit later. Capacity misses, how do you actually eliminate that? You utilize the cache space better. Basically, keep the blocks that will be referenced. So management of the cache actually helps with the capacity misses. And we're going to see some software management soon. Basically, you can divide the working set of a program, as opposed to requiring a program to work with a huge working set, divide it into smaller pieces, and those smaller pieces hopefully fit in the cache, and you arrange the computation such that computation happens on smaller pieces of data at a given time, such that you don't get cache misses while you're doing that sub-computation that you have divided the bigger computation into. So we're going to talk about that. So there's actually a lot of things that have been done to improve cache performance. And the main thing is main goals are actually three. There are three fundamental goals. You want to reduce the miss rate, you want to reduce the miss latency or miss cost, and you want to reduce hit latency or hit cost. And some of these go against each other, unfortunately. So reducing miss rate is good, assuming you don't increase the miss latency or miss cost, for example. We will see that. Reducing hit latency or hit cost is not easy in software, let's say. But essentially, all of these can be influenced by software, especially the miss rates to some extent. So we're going to see some software management very soon. But don't ever forget that all of these above together affect the performance. It's not just about the hit rate or miss rate. It's also about the miss latency, miss cost, and hit latency or hit cost also. Okay, so these are some things that you may see if you take an advanced course. How do you reduce the miss rate? How do you reduce the miss latency and cost? And how do you do the last one that we're not going to talk about? But let's talk about some software approaches before we move into some other examples. So I've already given you some examples of better replacement and insertion policies, management policies, but we've not talked about software as much. If you know that caches exist, as a software designer, you can actually do a lot. Let me give you some examples. You can restructure your data access patterns such that they're friendly to the replacement policy, for example. They're friendly to the set associativity, for example. You don't trash the sets. They're friendly to the cache size. You can restructure your data layout. And there are a bunch of techniques. We're going to talk about blocking first. Okay, so how do you restructure data access patterns? The idea here is very simple. You either destructure the data layout or the data access patterns. So let me give you an example over here. Assume that you have a vector x And you store this vector in a column major order. Basically, what does column major means? Consecutive, well, it's part of the matrix, let's say, sorry. It's not a vector, it's matrix, as you can see. It's a two-dimensional vector, in other words, two-dimensional matrix. Basically, if it's stored in a column major order, if you remember from the SIMD lectures, consecutive elements in the column are in consecutive location in memory, right? In other words, xi plus 1, j is the column index, follows xi comma j in memory, right? These are consecutive in memory location. So that's good. Ideally, these are in the same cache block, basically, because the same cache block is in the same spatial space. Whereas xi comma j plus 1 is far away from xi comma j, assuming this is a large matrix, right? Assume that that's a large matrix to begin with. Hopefully that's clear. This is the column major. We've seen this actually multiple times on SIMD lectures. So basically, given this, I would argue that this is very poor code. If you actually know that your processor is a cache, which all processors do today, you should not write this code, assuming your matrix is stored in column major order. Why? Basically, the inner loop over here is iterating over the columns. What it's doing is essentially is touching xij, and then xij plus 1, and then xij plus 2, xij plus 3, ... Basically, it's touching other columns, right? So you can fix this relatively easily by doing a loop interchange. You interchange the inner loop with the outer loop, and you still get the same sum, as you can see. Basically, this is much nicer. What you're doing is consecutive iterations of the inner loop is touching consecutive locations in memory, right? That's the idea over here. Okay, so this simple fix will actually buy you a lot of performance in real life. Of course, you need to know that there's a cache and this happens, right? Now you know that there's a cache and you can actually make your code much faster. So you should never write the poor code. But of course, this requires the knowledge of the data layout as well as the access pattern. So you need to think basically. It's not as simple as, okay, I write this code and it's beautiful. Okay, so let's go loop interchange. There are other optimizations that can increase hit rate, like loop fusion, array merging, etc. Compilers could be able to do this actually if they can disambiguate nicely, but it may not always be possible. Okay, let's take a look at another example, blocking. I've already given you the idea actually. Here, the idea is to divide the loops operating on arrays into computation chunks such that each chunk can hold its data into cache. It's kind of basically divide your program into smaller chunks such that the data that each chunk is operating is in the cache, right? It doesn't have cache misses. Now, this avoids cache conflicts between different chunks of computation. Essentially, you divide the working set such that each piece fits in the cache. At any given time, you're operating on different parts of the working set. This is also called tiling, loop tiling, or blocking, or matrix blocking, matrix tiling. There are many names for this. I'll give you an example from GPU, real code. You can actually watch a longer lecture from an earlier incarnation of this course. Essentially, we have same memory location accessed by neighboring threads. You can, for example, apply a Gaussian filter on every pixel of this image. If you're actually doing computations, if this is too big to fit in your cache, just do the computations that you need to do over here in a batch, and then you move to the next part, right? And then you move to the next part. That's the idea over here. So basically, to take advantage of data reuse, you divide the inputs into tiles that can be loaded into scratchpad memory into GPUs, but it could be a cache also in a CPU or even a GPU. And tiling is basically dividing this entire, let's say, matrix into smaller chunks where the size of the smaller chunks is smaller than the size of the scratchpad or the cache. Now, let me give you a real example. If you have matrix multiplication, you have matrix A, you have matrix B, you're multiplying A and B. Whatever you're doing is essentially a dot product of this vector row of this with this column, and you're generating the data point over here, right? Now, assume that these are in row major layout. If both of these matrices are in row major layout, while you're doing this accesses, this has good spatial locality clearly. So the cache hit rate of these accesses are nice. Unfortunately, the cache hit rate of this is really terrible, as you can see, because things are far away from each other. So basically, if you naively implement this using the entire matrices, you have poor cache locality for multiple reasons. One is what I just said, and also the size of the matrix may be very large. Essentially, the consecutive accesses to B are far away from each other in different cache lines. Every access to B is likely to cause a cache miss. So how do you reduce that impact? Essentially, you can achieve better cache locality by dividing each of these matrices into tiles or blocks that fit in the cache. It could be the cache actually. It could also fit in the scratchpad or the register file. Right? So let's take a look at an example. So assuming your tile sizes are determined to be this, such that this fits in the cache, this fits in the cache, this fits in the cache, and actually they all together fit in the cache. You should determine it that way. You can have very good locality over here and here. So, and then you move to the next blocks, right? So you basically do the computation of the points over here, all of the rows, all of the columns over here, and have some partial sum over here. And then you move to the next tile and calculate these points. And then you move to the next tile and calculate the same points and accumulate basically. So the hope is that you're maximally utilizing your cache space because you've determined the tile sizes such that whatever you're operating on, these 3 different tiles from 3 different matrices are in the cache at the same time, and you don't get cache misses. Makes sense, right? If your matrices are large, clearly you're going to get a lot of cache misses in this. Of course, this requires more work. Basically, this is the tiled implementation. You can see that the loop iterations are divided into tiles. Basically, you operate on sub-matrices as opposed to the matrices. And hopefully, these sub-matrices fit in the cache, scratchpad, register file. You can optimize for different levels in the hierarchy also. Okay, so that's basically what you do. You multiply small sub-matrices over here. Okay, if you want to know more, there are actually lectures that cover this in more detail, but we don't have time. Now, let me give you another example. So I've given you a lot of software examples so that you can actually do this. I'm going to give this example and then we're going to stop. But let's take a look at this example. You have a node. Assume that you have the database of people, and this is a linked list in this particular case. You have the name of the person and the school of the person. These are character arrays, as you can see. And you want to traverse this database. Let's traverse this linked list. Assume a huge linked list, 1 billion people in the world, all of the people in the world. Nobody should program like this, clearly, but assume that it happens. So basically, you're given a key, the name of a person. You basically check whether the node matches that input key. If not, you go to the next node. Basically, you're searching for a name in the entire, you're searching for a key essentially in the entire, or it could be the ID of the person, for example, right? You're searching for the key in the entire linked list. And if you actually find the key, find the ID, let's say, you print the name and school, for example, okay? Now, since we don't have time, I would normally ask this question. Does this code on the left have poor or good cache hit rate? And the answer is it has terrible cache hit rate because of this. So what you're doing is, let me take a look at, this is frequently accessed, and the other fields are actually not frequently accessed. So the frequently accessed data is blue over here. The likelihood of the key matching in this 1 billion accesses is very low, essentially, assuming you have unique keys. So this is not frequently executed code, not frequently executed data. So key and next are actually the frequently accessed fields, but name and school are not frequently accessed. So what do you do? Essentially, what we have done over here is with this data structure layout, all of these are in the same cache line, assuming a node is allocated spatially. It's allocated in consecutive locations. Next comes, this is maybe 4 bytes, int is 4 bytes. Now you have 256 bytes name. And your cache block can be 64 bytes. So most of your cache block is actually name, if you will. The key and the next is only a small fraction of your cache block. So while you're traversing this, you access one node, and then you get a cache miss to access the next node. So every node incurs a cache miss, basically. Okay? This could have been worse, actually. The layout may have been next and key may be separated from each other. So every node gets 2 cache misses, essentially. So basically, other fields occupy most of the cache block, even though they're rarely accessed. That's the problem. So the key idea is very simple. Once you realize that, what you do is, as a programmer, you could separate the rarely accessed fields into a data structure and pack them into a separate data structure. So these are the frequently accessed fields with a pointer to the rarely accessed fields, for example. And now you access 2 different data structures. Rarely accessed data structures here, frequently accessed data structures here. There is a small, not frequently accessed component. The general idea is basically separate the hot data from cold data. Hot data is frequently accessed, cold data is rarely accessed, such that they're not in the same cache block. That's the key idea. Okay, who should do this? Programmer in this case, but compiler maybe, hardware maybe. Who can determine what's frequently accessed is a great question, which we're not going to answer. Okay, so we're done. We're going to pick up from here tomorrow and talk about prefetching. So let's get started. We're going to continue on caching. We've covered a lot of caching issues yesterday, but there's more to cover. This is actually a fascinating subject. And people have worked on caches for decades, as I said. There's a famous conference in computer architecture, International Symposium on Computer Architecture. Sometimes people joke about this conference saying it's International Symposium on Cache Architecture. CA, Computer Architecture, Cache Architecture. I like that joke, but I don't think that's true anymore, let's say. It used to be true at some point. There were so many caching papers, but right now there's a lot of diversity in the topics. Okay, so I want to cover some caching issues that we couldn't cover yesterday. These are the same readings that you've been doing. And we're talking about the cache hierarchy. And we talked a lot about the design decisions within a cache as well as across cache levels, right? And I also stretched your mind yesterday saying that cache hierarchy or memory hierarchy extends beyond a single server. But within a single server, memory hierarchy also extends. You can see that there's hybrid memories that are happening today. You can see main memory like DRAM, but then main memory is also expanding within a single server with additional type of memories like phase change memory. But this could be different types of DRAM also. This could be, for example, high bandwidth memory, and this could be some other types of DRAM. So you can see that there's heterogeneity that's happening in the memory hierarchy as well. And in many cases, the proposals are such that there's a fast DRAM that acts as a cache for a larger DRAM or larger phase change memory, if you will. Does that make sense? So you can see that there's a lot going on. So never think that this is a static system where it looks like this, but things are changing around here. Things are changing around here. Things are changing also across the network so that the main memory is expanding across the network, if you will. So that's why caching is extremely important, actually. Caching actually takes place in all of these different memories. All of these memories can be viewed as caches. So DRAM is really a cache for the storage system, as we will actually see in the next lectures about virtual memory. Okay, so recall what we discussed. Yesterday, we talked a lot about issues in set-associative caches, especially decisions that we make for insertion, promotion, and eviction replacement. I will not go over these again. I hear some echo. Is it because of me or is it because of something else? Okay, there's this noise, tuck. I saved the computer also. Okay, and then there's also design decisions that you make across the cache hierarchy in multi-level caches, right? So we've discussed these as well. We couldn't cover all of the design decisions, of course, but you can imagine there are many other design decisions that you need to make. So we also were covering different options for improving basic cache performance. There's a lot to cover here. You actually talked about a bunch of these over here. And we were talking about software approaches. We finished the software approaches. There are more software approaches you can talk about, but otherwise we will be spending, we'll be renaming this course to Digital Design and Cache Architecture. Let's not do that. But let me cover some things that are not, let's say, challenge the conventional wisdom, which is going to be this cost of cache misses. So if you think about miss latency or miss cost, what is that affected by? We discussed this, but let's take a look at it in a bit more detail. So this is affected by two things. One is, where does the miss get serviced from? Does it get serviced from the next level, etc.? We'll see that. And how much does the miss actually stall the processor? In the end, the most important one is the second one, actually. But I will kind of try to break down these two things into separate pieces. So the miss can get serviced from the next level in the cache hierarchy, right? If you get an L1 cache miss, the next access to the L2 can be a hit for that. Then it's a short latency cache miss, right? But the miss actually can go out all the way to remote memory. In that case, it's actually a long latency cache miss. And then if it actually goes to DRAM, it could be a row hit. Remember the DRAM lecture that we had? You can have a row hit versus row conflicts. You can have conflicts in the rank channel. All of those actually increase the latencies of the cache miss that you're trying to bring into the cache hierarchy. So there are different latencies depending on where you hit in the hierarchy, where you hit in the DRAM, whether you get a conflict on the bus, for example, or not. And you can have queuing delays in the memory controller and the interconnects if you're going to a remote memory in the network. So there's actually delays that you experience. These all affect the latency of the miss. And as we discussed, local versus remote memory. Does the miss get serviced from the chip, from the same node, from the same rack, or some remote server, some memory blade, for example, that's far away? that all affects where the latency. And there could be other things that you can add over here. And the second thing that affects the missed latency or missed cost or experienced stall time is really this stall time, experienced stall time. This is affected by whether the miss is overlapped by other latencies, whether the data is immediately needed by the processor also. So you may actually require a cache miss, but you may not need the data immediately. For example, this could be a cache miss because of a write request, and the processor doesn't need to stall because the write request, the result of the cache, the cache block is not needed for a dependent instruction immediately. That's different from a load instruction. For a load instruction, you get a cache miss, and the data is not available, so the dependent instructions cannot execute. That hopefully makes sense, right? And then there's also other issues like that affect the cost of a cache miss. What are you going to evict, right? Is this more costly than some other cache miss that's going to be longer to refetch if it's needed later on, if you're assuming that you evicted it? So you can see that once you start talking about missed latency and missed cost, especially, this starts becoming a bit more hairy. There are a lot of different things that get into play that affect how long does the cache miss take to service, and also how much of that latency is actually exposed to the processor as stall time in the end. Does that make sense? And these are not easy to determine. So, but let's take a look at one example of this. So this is the notion of memory level parallelism, and I alluded to it in an earlier lecture, but we never really looked at it. But modern processors can actually have different types of cache misses. So if you look at this cache miss over here, it's isolated. There is no other cache miss that is happening at the same time over here, which means that this is the latency of this cache miss is fully exposed to the processor, assuming it stalls the processor, right? That's the assumption. But these two misses are serviced in parallel. You generate cache miss C and then cache miss B, and then they're serviced in parallel in different banks, for example, in DRAM. As a result, their latencies are overlapped. So that's the notion of memory level parallelism. It's really the notion of generating and servicing these multiple memory accesses in parallel. Now, if I tell you, if you eliminate one miss out of these, which one would you eliminate to improve performance? These are the only three misses in your processor. If you want to improve performance by eliminating only one miss, if you had the option to eliminate only one, which one would you eliminate? Anybody? Don't be shy. Yes. A, exactly. So if you eliminate A, what happens is this, whatever request that is a miss right now will become a cache hit. You eliminated it. So the processor can continue processing, right? That's not true for B or C, right? If you eliminate B, the processor will still store for C because it's waiting for C. We're assuming that it's really waiting for the data to come back to proceed, right? If you eliminate C, the same thing happens. The processor still needs to stall for B. So if you really want to get rid of the stall time due to the second parallel misses, you have to eliminate both B and C. So eliminating A is roughly equivalent to eliminating B and C together, which means that A is a much more costly miss, right, from the perspective of performance compared to B and C, and B and C are less costly. And this makes sense because what you're doing is you're parallelizing things. As you parallelize things, you're tolerating the latency of each of the misses, right? We talked about out-of-order execution. And in out-of-order execution, you're parallelizing different operations, meaning each operation appears less costly to the processor. So that's the fundamentals of real latency tolerance. Okay, so hopefully this is clear. So basically, there are many techniques that are proposed to improve memory level parallelism. Out-of-order execution is one of them. And we've seen that out-of-order execution is able to do this actually. It can generate different cache misses in parallel, and they can be serviced in parallel in the main memory system. But this also leads to some misses being isolated, some misses being parallel, and there's different levels of parallelism, right? I could have another example over here where you have 8 misses serviced in parallel, and eliminating any of them will not actually buy you almost any performance unless you eliminate all 8 of them at the same time, right? Roughly, right? There's of course trailing edges and leading edges of misses, when they start, when they end, how long they take. They're not always equal, like this nice picture depicts as well. Okay, so the cost of a miss is affected by which other misses it is serviced with, or how much memory level parallelism there is while the miss is actually being serviced. Now, the question is, how does this affect cache replacement? This clearly affects a lot of things, actually. I'm happy to talk about it some other time, perhaps, but let's look at cache replacement since we're talking about caching. So basically, the issue is traditional cache replacement policies, whatever we talked about yesterday, it doesn't take this into account, even though this is actually important. And the realization of this is actually very interesting. They make this implicit assumption that reducing miscount reduces memory-related stall time. If you reduce miscount, that's always good for performance. I kind of foreshadowed in prior lectures saying that this is not necessarily true, right? So essentially, misses with varying cost or memory level parallelism in this particular case breaks this assumption. If the misses are not equally costly, this assumption is broken to begin with. So then the question is, how do you actually design a cache replacement policy that takes this into account? This is still low battery, by the way. Anybody? I don't know, you plugged it in, but I don't want the lecture to stop again. How long? Are you going to help or? Okay, power source battery right now. Looks like it's working. I don't know, is it working? It's not working. You have another one? Okay. Okay, I mean, this is working, but you can keep it over there, thanks. I don't know how that got disconnected. Let's check it once more. Okay, something is happening, but let's stop sharing. Okay, let's go back. Okay, so we were here. Basically, any misses that have varying cost or memory level parallelism breaks this assumption, as we discussed, right? And as we just discussed, eliminating an isolated miss helps performance more than eliminating a parallel miss. And eliminating a higher latency miss could help performance more than eliminating a lower latency miss. I said could over here because latency is not necessarily directly exposed to the processor, right? It also depends on how much you have tolerated that latency. So I'm not going to give you a solution to this, but I want to emphasize this because this is actually becoming a lot more important in existing systems with very sophisticated memory hierarchies, with very sophisticated prefetchers, as we will discuss. You cannot ignore these stall times or the cost of a cache miss anymore, essentially. It's really, we need to really rethink the design of the caches such that they don't make this assumption. They basically don't take, they actually take the miss cost into account. Now let's take a look at an example. I like this example. When we constructed, actually, I was quite happy. So if you look at this example, what we're going to look at is a cyclic access pattern. The processor is, these are blocks to the same set, basically. Assume that this is your cache. You have only 4 blocks in your set, and that's your cache. You don't have anything else. And this is the access pattern that we're going to see to the cache. Basically, blocks P4, P3, P2, P1 are accessed in this order. And then you touch blocks P1, P2, P3, P4. And then you touch blocks S1, S2, S3. And then this access pattern repeats, as you can see. It's a nice cyclic access pattern, like we have seen. The difference between P and S is P misses to blocks P1, P2, P3, and P4 can be serviced in parallel. And misses to blocks S1, S2, and S3 are isolated. Hopefully that makes sense, right? So basically, these misses are less costly from the processor's perspective. These misses are a lot more costly. Eliminating S1 actually stops the stall of the processor completely. Okay, now let's take a look at 2 replacement algorithm. One that minimizes the miscount optimally, which is Bell-D's optimal. If you remember, Bell-D's optimal replacement policy replaces the block that's going to be referenced furthest into the future. And that's why it's optimal. You can prove it. And we're going to also look at the MLP aware policy, as we call it, that actually targets these isolated misses and tries to keep them in the cache. Tries to keep blocks S1, S2, and S3 in the cache. And we're going to look at a fully associative cache containing only 4 blocks, a single set, if you will. You can also think about it that way. So basically, what we're going to demonstrate is that fewest misses is not going to lead to the best performance in this sort of access pattern. And how do you demonstrate that? Let's look at Bell-D's optimal. So Bell-D's optimal, if you actually do the analysis, all of these should be hits in the steady state. I'll let you think about that. But assume that we start from that steady state. These 4 accesses are hits, and the state of the cache at this point is P4, P3, P2, P1, because you've touched these. Clearly, these should be in the cache at this point, according to Beldy's optimal, right? That makes sense, right? That's the starting point, which means that the next accesses are all cache hits because they're essentially touching the cache blocks in the cache. Fine. Now, when you get to this point, the cache looks like this. P4 is the most recently referenced. P1 is the least recently referenced, but that doesn't matter with Beldy's optimal. With Beldy's optimal, you ask the question, whenever you see S1, S1 is going to replace the cache block in the cache that's going to be referenced furthest into the future. Now, what is furthest into the future among these? Well, P4 is the first into the future, if you actually go and follow the cyclic pattern. P3 is the next, P2 is the next, and P1 is the furthest into the future, as you can see. So P1 will be replaced by S1. Of course, this is a miss because it's not in the cache. So now S1 is in the cache. Now again, S2 is not in the cache, so S2 is going to replace the block that's going to be referenced furthest into the future, which is going to be P2, if you do the same analysis. This is a miss. It's sorry, not P2. It's going to be S1 actually, right? You're going to replace S1 because S1 is going to be replaced furthest into the future, right? Because P2 is going to be referenced before S1. So we're going to replace S1. So S2 is going to replace S1, and similarly, S3 is going to replace S2 at this point. So you get misses in this S1, S2, and S3, and they're going to replace each other. And then when you get over here, you see P4, that's a hit, clearly. So these three are going to be hits because they're P4, P3, and P2 are in the cache. S3 is in the cache, and now you have P1. P1 is a miss because it's not in the cache, and P1 is going to replace S3 because S3 is the one that's going to be referenced furthest into the future because you're going to reference P1, P2, P3, P4, all of them over here. Okay, so that's basically gets us back to the steady state. And if you look at the execution time of this, there's one miss here, which causes some amount of stall. Assume that it's some uniform amount of stall. Here, there's all hits. This unfortunately doesn't align too well, but if you look at this, there's one miss over here, one miss over here, one miss over here, one miss over here. So you have 4 misses in total. And you have 4 stalls, right? Because they're kind of isolated stalls. Here you have hits, so you don't stall for any of these. So that sounds good. This is basically the analysis with Beldy's optimal. You should be able to do this analysis and reverse engineer all of that. And there are beautiful cache questions that you can solve in the homework, etc. I have a favorite question, but I'm not going to tell you what that is right now. Okay, not related to this actually. It's related to the cache structure. Okay, so this is optimal. Optimal for minimizing miss rate. Let's take a look at what a cost-aware or memory-level parallelism-aware replacement policy would do in this case. Basically, the purpose of this replacement policy is to keep these S1, S2, and S3 in the cache as much as possible, right? Because they're much more costly. We would like to eliminate them, eliminate the misses caused by them. We don't care as much about these because they're not very costly, as you can see, as we have discussed earlier, right? That's the theory. So basically, at the steady state, this MLP-aware replacement policy should keep S1, S2, S3 in the cache at this point so that you get hits in all of these, right? And that should be doable, hopefully, with some heuristics, etc., which I'm not going to go into. But I'm going to demonstrate the issue or the benefit of this replacement policy. And based on some heuristics, maybe P4 is in the cache because that's the last thing you touched over here, okay? So this is the steady state. Now, you get hits in S1, S2, and S3 as you access them over here. When you go over here, you go back to the cycle, you want to keep S1, S2, and S3 in the cache. As a result, you get 3 misses over here, right? There's a hit in P4, but P3, P2, and P1 miss. Okay. Maybe you replace P4 with P1 because that's the last referenced. In this case, you get a hit on P1, but P2, P3, and P4 miss. So you see that now we had 6 misses, and you get back to the steady state. So now we had 6 misses over here. But you have only 2 stalls, let's say approximately. As a result, this is a much better replacement policy because it saves cycles, as you can see, right? You got rid of the stalls. You got rid of 2 stalls, basically. Make sense? So that's the importance of cost of a cache miss, essentially. Now the question is actually, how do you take this into account? How do you actually make it work? That's for a further course. If you're interested in this, and there's a lot of interesting things that can be done in this area. This paper shows this example also, actually, and you can take a look at it. Basically, how do you incorporate this cost into replacement decisions? How do you design a hybrid cache replacement policy? In the end, the replacement policy turns out to be hybrid because there are some access patterns that benefit a lot from, let's say, recency cost-based replacement, and there are some access patterns that benefit a lot from cost-based replacement, and you need to incorporate them somehow. But again, I'm not showing you the policy over here. Okay, so this, I think, brings us to the somewhat end of what I want to cover in terms of cache performance. There's a lot more to cover over here, but we don't have time. If you're interested in this, there's a lot more material in future courses and also online out there as well. And also lectures, as you can find out. So we didn't cover some ideas like victim cache. I think these are interesting, but they're a bit old for today's systems. If you're interested, you can take a look at the lectures. But there are other ideas that are quite interesting, which we're not going to cover today. Any questions? Was that example convincing? Did that convince you that you should really not optimize just for miss rate? Okay, good. Yeah, I think it all boils down to coming up with fundamental examples like this. That's how you can improve systems in the end. So it basically boils down to doing stuff on pen and paper and figuring out what you should really improve. Okay, so let's talk about multi-core issues in caching. I want to spend some time over here because multi-core imposes a lot of other interesting issues in caches. And as we discussed, all of our systems are multi-core, right? So in this system, for example, L1 caches were private. I believe L2 caches were also private. L3 cache was shared across processors. So even that's a design decision that you need to make, right? Which caches are shared by which cores? And then do you design higher level caches that are shared, etc. So you're used to these pictures right now. I will mention this cache over here because it's very interesting. This is a shared cache that's on a different chip. So basically, they've decided to add these other, let's say, other chips that are bonded on top of a processor chip. And the whole purpose of the other chip is to cache. And there are a lot of actually really interesting technology issues, like how do you align the interconnects in this chip with this chip over here so that they can actually communicate with each other nicely. So there are a lot of fabrication and reliability issues over here that we take for granted right now. But these are two different chips bonded together on top of each other. And the whole purpose of the second chip is just caching, basically. Caching for all of those cores that are in the other chip. And there are many cores over there. Okay. So basically, cache efficiency becomes a lot more important in a multi-core or multi-threaded system. If you have a single thread accessing the cache, that's nice, you can manage it. But then if you have 10 different threads or 20 different threads or 100 different threads accessing the same cache, now you got to be a lot more efficient. The same is true for memory bandwidth. Actually, memory bandwidth is even more important potentially. So that's why there have been a lot of research in multi-core systems or caching for multi-core systems. Basically, memory bandwidth is at premium. You don't want to go to main memory. You want to basically ideally hit in caches. Unfortunately, it doesn't happen. And also, a cache space is a limited resource across cores and threads. So both space and bandwidth are problems. Then the question becomes, how do we design caches in a multi-core system? There are actually many, many interesting design decisions over here. Should they be shared or private across cores or threads? We're going to look at this one. How do you maximize the performance of the entire system as opposed to just a single thread that we've been talking about so far? How do you provide quality of service to different threads? How do you provide predictable performance? If some thread, for example, needs really hard deadlines, because it could be a GPU, for example, it needs to display a frame on a video frame, for example, on the screen. And if you actually skip some things, that's not going to be great for the quality of service provided to the user. It could be a safety critical thing also. Basically, there are a lot of interesting issues over here. Should the cache management algorithms be aware of the different threads accessing them? Right. We have not talked about this so far, but maybe yes. And how should space be allocated to threads in a shared cache, assuming that you actually want to do this space allocation across different threads? And then there are other issues, like if the bandwidth is at premium and if the space is at premium, should you actually start compressing the data that's in your caches? It's actually, I think, an important area. And people have been looking at compressing data inside the caches, compressing data inside the memory so that they can actually store more data, reducing the redundancy and waste in the data. And also, how do you do better reuse prediction and management in caches? We've been talking about reuse prediction and management, but you need to do better in all of these. And there may be other questions also. But let's take a look at one dimension of this, which is basically, should the cache be private or should the cache be shared across cores? Or a subset of cores, right? You could generalize this. So a private cache, a cache belongs to one core, which means that a shared block can be in multiple caches. Right? Whereas a shared cache is shared by multiple cores. Basically, the L2 cache over here is shared by multiple cores, as you can see. And if there is a block that's shared across those different cores, it doesn't need to be replicated across different caches, essentially, if the cache is shared. A block is in only one place, essentially. So you can see there's one immediate advantage of a shared cache. It reduces the replication across different private caches, right? So I'm not even talking about L1 caches, as we discussed yesterday. L1 caches are very tightly coupled with the core. So the design decisions are usually, oh, it's obviously private, right? Because it's part of the core, right? Whereas L2 cache is outer cache. So maybe it's not private, maybe it's shared. Today, some L2 caches are private, some L2 caches are shared, but L3 caches are almost always shared today. Well, I should probably say always shared. Okay, so basically, this is the concept of resource sharing. So if you look at the private caches over here, you're dedicating the cache to the core, and each core has a cache associated with it, L2 cache. But if you look at this other shared cache, you're sharing the resource. Instead of dedicating a hardware resource to a hardware context, more generally, we allow multiple hardware contexts to use it. So it could be core, it could be thread, because we can have multi-threading within a core also, right? So it's good to think about this. Essentially, that's the concept of resource sharing. And the resource sharing can be many things. It could be functional units that are shared. It could be the pipeline that are shared. If you remember the fine-grained multi-threading, we shared the pipeline, we shared the functional units, we shared the entire pipeline, essentially, across different threads. It could be the caches, as we've discussed, but also it could be the buses, memory, interconnects, and storage. A lot of those actually are shared across threads because they're too expensive to replicate. Buses are expensive, memory is expensive, interconnects and storage are expensive to replicate. So you do share them across different threads. Caches are, some of the caches may not be too expensive to replicate. So what is the benefit of resource sharing? Why do we share resources? Because it improves utilization and efficiency. That leads to higher throughput, higher performance. Why? Because when a resource is left idle by one thread, another thread can use it, right? There's no need to, and also there's no need to replicate shared data. These are two different things, actually. I've given you the example of instruction versus data caches yesterday, right? If you actually partition them, it's the same example, basically. You have two different cores, core 1 and core 2. If you actually have private caches of 64 kilobytes each, one core may be using 1 kilobyte of its own private cache, another core may be needing 127 kilobytes. But if you dedicated 64 kilobytes and partitioned it across different cores, the core that needs 127 kilobytes would be unhappy. The core that needs only 1 kilobyte would be happy, but it would be underutilizing its cache. So you'd basically waste space because of this. If you had a shared 128 kilobyte cache for both of them, both of the cores would be happy and you would not be wasting space, right? And you would not be increasing the execution time with the same amount of resources. So basically, that's the advantage of resource sharing. It improves the utilization and efficiency, and hopefully that improves performance in the end. And also, there's no need to replicate the shared data, which we also discussed, which we're going to discuss when we talk about cache coherence as well. But there are other benefits, which one benefit is it reduces communication latency. Data shared between multiple threads can be kept in the same cache in multi-threaded processors, for example. If you have a shared cache, for example, you don't need to go to some other cache to get the data that's shared with someone else. As we will see in cache coherence, you may need to do that, actually. It's in a shared location. Everybody accesses that from that shared location. It could be in the L2 cache, but you could also think about this in the L1 cache, right? In the L1 cache, you have multiple threads, and multiple threads are sharing a cache block, and they can access it quickly from the L1 cache. Okay. And also, this is compatible with the shared memory programming model, because in shared memory programming model, different threads actually communicate with each other using load and store instructions. One thread stores to a location, another thread reads from that location. Have you guys seen the shared memory programming model in any courses? Parallel programming? Not yet? Somewhat? Okay. Who has not seen it? Okay, some people have not seen it. Who has seen it? Okay, we see almost 50-50 over here. who may have seen it but doesn't remember if they have seen it. Okay, that's good. It's good. It's good that you're honest. But in shared memory programming model, memory is shared across different threads logically and also physically normally. But whenever a programmer writes a program, a thread can do a store to a memory location. Another thread can see that store and load from that memory location. That's how you can synchronize between the threads, for example. We're going to look at that in cache coherence also. And this is sharing of a cache is very compatible with that model, right? That model says there is a single memory, and anybody can see that memory, read from that memory, write from that memory. It doesn't talk about replication of memory, right? Caches, private caches are essentially replicating pieces of that memory locally next to the processor. Right? So it's, in a sense, it's not, from a principled perspective, it's not compatible with that model. Of course, it's compatible in the sense that this is all under the hood, right? You're still obeying the shared memory programming model from the software perspective. Okay, so these are actually the advantages. But unfortunately, resource sharing has disadvantages as well. One of the major ones is it actually results in contention for shared resources. When the resource is not idle, another thread cannot use it, basically, because somebody occupied that resource. Right? That's true for any kind of resource. It could be cache space. It could be bus bandwidth. It could be some memory space. It could be some storage space. Basically, if the space is occupied by one thread, another thread needs to reoccupy it if it actually wants to use it. And this leads to reduction of performance. It could reduce each thread's performance. It could reduce some threads' performance. If you're lucky, maybe it doesn't reduce anyone's performance because the block you're evicting is not going to be reused by the thread that occupied it earlier, right? For example, right? But usually it leads to some performance reduction for some thread or all threads. Basically, thread performance can be worse than when it's run alone, and that's actually true in many cases. The other issue, which is different from this is performance degradation. But the resource sharing, if it's not controlled, leads to performance isolation or eliminates performance isolation. Basically, you get different amounts of cache space, for example, allocated to you based on who's running together with you in the shared cache, right? You may be running with different applications at different times. So you optimize this beautiful application that you wrote it very nicely. You fit it in the cache, in the L2 cache you thought you would have. And when you run it with application A, you get that amount of cache, so your performance is great. When you run together with application B, that application B is very aggressive. It kicks out all of the cache blocks that you need to have in the cache because you optimize your program, and your program's performance is terrible. So this eliminates performance isolation. The programmer was programming or optimizing for hardware, assuming that it would get some amount of cache, right? But you didn't get that amount of cache because the resource was shared across different threads. And the program has no control over that, clearly. The system has control over which threads are scheduled with each other. And as a result, all of your optimizations are essentially useless, let me put it that way. So that's the importance of performance isolation. You may optimize your program, and you may not, if you get performance isolation in the resources, meaning that you actually get the assumed resources in hardware, then your performance is predictable across different runs. Okay, so this is the downside of not having performance isolation because you get very inconsistent results in terms of performance. And also this regrades quality of service, which is related to performance isolation. So if you don't control this sort of sharing, you can have unfairness or starvation. Essentially, some thread may be hogging the resources, and another thread can be delayed indefinitely, if you will. We're going to see examples of this maybe in a later lecture, but I'm going to actually show you an example with the caches soon. So we could keep adding some more over here, but basically you need to efficiently and fairly utilize shared resources. If you're actually doing resource sharing, if you say I'm going to share the cache, you need to have mechanisms to do this efficiently and fairly, such that you get quality of service and you get performance isolation if it's needed for the programs. Again, we're not going to go into how to do this. I'm just foreshadowing some of the problems that exist in modern systems. In fact, some processors have quality of service mechanism incorporated into them right now. Intel, for example, has a way of partitioning the cache across different applications, and some amount of control on partitioning the memory bandwidth as well. This didn't exist actually 15 years ago, etc., or even more recently, maybe 10 years ago. Okay, now let's analyze this private versus shared caches from this resource sharing perspective. As I said, private cache belongs to one core. Shared cache is shared by multiple cores. So what is the advantage of shared cache? You get high effective capacity. Anyone can utilize this big cache, right? That's good. You don't basically, you don't have this fragmentation inside the cache. Because you dynamically partition the available cache space, there's no fragmentation due to static partitioning. And if one core doesn't utilize some space, another core can. So this is nice, clearly. And it's also easier to maintain coherence. We're going to talk about that. Because a cache block is in a single location, right? It's not replicated across caches, which means that if one processor updates it, it's fine. Everybody sees that update because it's shared, right? So that's good. And we're going to see coherence a little bit more. So the disadvantages, actually, we have not talked about this, but if a resource is shared, you cannot customize it to the to a single processor, for example. Whereas if you have a private cache, you can customize it, you can couple it tightly with the core, and it can actually have very high throughput. Whereas it's shared, you need to have some sort of network to communicate between the cores to the cache, right? Assuming the cache has a lot of banks, for example, to service. So basically, you get slower access in the end. And as we discussed, cores incur misses by evicting each other's blocks, essentially. These are misses due to inter-core interference, if you will. And some cores can destroy the hit rate of other cores, basically, depending on the access patterns again. Right? One core may have very nice locality in the cache, but it may be using, I don't know, 10% of the cache, shared cache. A very small amount of cache. It may need a very small amount of cache. The other core may be streaming through memory, and actually it needs 10 times the size of the cache. When they actually share the cache, the second core actually kicks out all of the blocks that the other core would otherwise have if it were actually running alone in the system. So basically, that's what happens. I'm going to demonstrate this pictorially as well. And essentially, guaranteeing a minimum level of service or fairness to each core becomes harder because of this sharing. How much space do you provide? How much bandwidth do you provide? You need to answer these questions, actually, when you're designing the resource. Okay, let me give you an example. Basically, if you look at this example, we have two cores, very simple. Thread 1 is running on this core. And when it's running, it demands almost all the cache, as you can see, L2 cache. Thread 2 is running on this other core, and it demands some of the cache, let's say, when it's running alone. And when they run together, thread 1 occupies most of the cache because it may have a very intensive access pattern, right? And as a result, thread 2 gets much less than what it really needs to get high performance. Maybe it gets nothing almost, right? Because thread 1 actually can be very intensive in terms of memory accesses, so it could be generating 10 requests at the same amount of time. T2 is generating 1 request, for example, right? It could be 100, actually. It could be very, very widely different. As a result, thread 2's performance may be significantly reduced due to this unfair cache share. And this is a real problem in existing systems. That's why you need to design the resources to be shared, assuming you want the benefits of sharing. But also, you should not allow this to happen in existing systems. Okay, I could go on and on, but unfortunately, we're not going to go into how to do that. Basically, resource sharing and partitioning are at odds with each other. Sharing improves resource utilization, for example, better utilization of space. Partitioning provides performance isolation or predictable performance because it dedicates space to a single thread or a single core. The key question is, can we get the benefits of both? And the idea is basically have sharing in the resources, but design mechanisms in those shared resources such that they're efficiently utilized, controllable, and partitionable. So you need to have mechanisms to have controlled sharing, essentially. And the hope is that this way you have no wasted resource, which is a problem with dedicated space, partitioning, and you have quality of service mechanisms that you added to avoid the problems that you have with sharing. Okay? Unfortunately, you're not going to get the perfect upsides of both, but you're going to get most of the benefits of both if you do this. And again, we don't have time to go over this. These are more advanced topics, but you can look at future slides or take courses, etc. Actually, there's a lot more over here. I don't have time to cover, but these issues exist whenever you have shared resources. And in modern systems, resources inside a core are shared across threads. So there's resource sharing inside the core. There's resource sharing outside the core. And outside the core, after some point, everything is shared across many threads. Imagine you have thousands of 10,000s of threads, and they're really sharing a memory. And memory bandwidth is limited. This is what we see in today's multi-core systems and GPUs, for example, or machine learning accelerators. So basically, there are a lot of issues that you see today. Okay, so let me give you another dimension over here, which is cache coherence. How many people have learned about cache coherence? Let me ask you the same questions. How many people have not learned about cache coherence? How many people may have learned about cache coherence, but they don't remember? That's okay. Okay, so let's learn about cache coherence because this is important. So basically, we have the shared memory programming model, as we've discussed. Threads and parallel programs communicate through shared memory. Thread 0 writes to an address, and thread 1 reads from that address. This implies some communication between two. This is how you can communicate between threads. And also processes, right? Processes are actually larger entities which may contain many threads. So this is one example. This thread is running on processor 0. It's writing to memory location 8. This thread is running on processor 1. It's printing memory location 8. So there needs to be some communication, as you can see over here. If this is the model, each read that happens should receive the value last written by any processor, right? Otherwise, you'll have inconsistency in the program. And there needs to be some proper synchronization between the threads, which we're not going to get into. That's a higher level concern. Basically, the programmer needs to synchronize these threads such that there should be an agreement among the threads as to what does last written mean, right? You use locks, barriers, etc., to do this synchronization, which we're not going to cover here. So we're going to cover the issue with caching. Basically, if you have memory location A that's cached in either processor, we have a problem basically, because the processors may not see the updates of other processors unless you do something special, which is called cache coherence essentially. So the basic question is, if multiple processors cache the same block, same cache block, how do they ensure that they all see a consistent state for that particular cache block, right? So we have two processors over here, processor 1, processor 2. They have private caches, cache 1 and cache 2. And there's some network through which they communicate to main memory. And we're going to look at this particular cache block X, whose value is initially 1000, right? So let's take a look at what these processors do. Let's say processor 2 loads X into some register, or part of X into some register. Let's say the value it loads is 1000. That's nice. The X gets cached. What is that sound over here? Am I doing this or? No, it's just the tick tick sound. I don't know. Maybe this is too close. Okay, so basically, this location X gets cached in this cache. And let's assume that processor 1 does the same thing. It loads X into its own R2, and this location gets cached over here. And then processor 1 does something else. It basically does updates location X. And this update gets reflected in the cache. It's a write-back cache, let's say. Now you have inconsistency, right? Main memory is not updated, and this cache is not updated. Then the question is, what should this processor load? When it loads X, should it load 1000? Actually, the easiest answer is should not load 1000. But this also depends on something else, which I don't want to get into, which is the memory consistency model. But the intuitive answer is really this should not load 1000, right? Because the value got updated before you actually should read 1000, right? You should really get the most up-to-date value, assuming the program is synchronized in a particular way. Makes sense, right? That's the intuitive answer. There is a much more complicated answer that requires you to really understand memory consistency, but that's something you should really look at in advanced courses. Okay, so a basic idea is how do you actually ensure that this processor doesn't load the wrong value? That's the basics, basically. Well, the first idea is basically whenever this processor does a write, it broadcasts that it's going to do a write to that block, and everybody who has the block in their cache invalidates the block. Right. This is a very basic cache coherence protocol. It's a broadcast-based cache coherence protocol. You should not write to this block until you're sure that everybody has invalidated the block. Right? That's one answer. The other answer is while you're writing to the block, you also write to all of the other cache's blocks. Basically, you broadcast the fact that you're writing and also the data that you're writing. Here, update your cache block because I'm writing to it. That's the idea. So that's the idea of a broadcast-based protocol. A processor or cache broadcasts its write or update to a cache block to all other processors. And another processor or cache that has the block either invalidates or updates its local copy of the block. Right? So then the question becomes, do you invalidate, do you update? We're not going to get into that. That's a more advanced question. But if you invalidate, that's enough, basically. And if you ensure that there are no race conditions, meaning that someone else doesn't read the old value of the block before that write actually happens, then this should be okay. Okay, that's the idea, basically. And this works nicely if the processors are connected through a medium or caches are connected through a medium where broadcasts are immediately visible to all of the other caches, which is essentially a wire, right? Which is a bus in this case, okay? That limits the scalability of these protocols in general. So let me give you a very simple cache coherence scheme. I'm not going to go into the detail, but because it implements whatever I said, basically. Whenever a processor writes to a cache block, it sends a broadcast message saying that I'm writing to the cache block, and everybody else invalidates the cache block if they have it in the cache. So all caches somehow observe each other's write and read operations. If a processor writes to a block, all others invalidate the block. So a simple protocol with some assumptions. You can study this on your own. Local processor can do read or write to the cache block. And based on those actions, bus read and bus write, are broadcast on the bus for the block. And this is what the protocol looks like. It has two states. Because it's a write-through cache, it doesn't have a dirty bit. That's the simplest protocol. So basically, you have a valid state or invalid state. If a processor writes to that cache block, it has to be valid, hopefully. Then it sends a bus write signal. This is the input, this is the output. And whenever a processor sees a bus write in its valid state to a given block, it makes the block invalid, right? This is a very simple state machine that you're used to right now. Right? And that's the idea, basically. With these assumptions, this is a working coherence protocol. And you didn't really increase the number of bits that you have in the valid bits, let's say. Normally, in coherence protocols, you actually need to increase the number of bits, if you will, because you may need to track modified, for example, and exclusive, etc. But we don't have time to discuss all of that. Makes sense, right? Okay, let me give you another coherence protocol. We'll not go into a lot of detail, but I have to cover this because modern protocols are a combination of both. They're both broadcast-based, but they're also directory-based. So the idea in the directory is have a middleman. Have a middleman arbitrate updates to a cache block or request to a cache block. And that middleman is called the directory. That middleman is logically centralized. But of course, if you want to scale a system, you don't want centralized components. So that middleman is usually physically distributed across different memories, but we're not going to talk about that. Essentially, imagine a central directory that keeps track of which caches contain every possible cache block. Every cache, before doing something to the cache block, consults this directory and asks for permission. Basically, I want to write to this cache block X. Can I do it? It basically goes to the directory. In this case, it's next to the main memory, but directory can also be cached actually next to the caches. So that's very fascinating. You can cache the directory that provides cache coherence. So caching is so powerful because this is actually huge. This thing is huge. And if you take the computer architecture course, you'll calculate the size of it and you'll see that it's huge. But basically, whenever you're writing to X, processor 1 wants to write to X, processor 1 says, I want to write to X directory, please give me permission. And the directory says, okay, let me see who else has X, because it has a bit vector that keeps track of which other caches in the system actually have X, which means that you need to have a bit vector or some data structure for every single cache block in the system to keep track of who has that cache block in their caches, right? Assuming that you have that data structure, directory says, oh, I think I know that cache 2 actually has cache block. I'm going to send a message to cache 2 and ask cache 2 to invalidate that cache block. And after it receives responses from all of the caches that have the cache block saying that they've invalidated the cache block, directory tells cache 1 or processor 1, go ahead, you can write it. You have the only permission or the only copy. Makes sense, right? So this is basically a middleman. Clearly, this middleman is costly because you're going through a middleman, this is an indirection. And as a result, the latency of this coherence scheme is much longer than the latency of what we have discussed over here, right? Here, one processor broadcasts, everybody sees, you don't need to go through any middleman. So that's much lower latency. But this is not scalable because if you want to actually have 200,000 processors connect to a single bus, good luck with that. Even more than 16 is not easy, unfortunately, today. But we have today multiprocessors that are on the orders of tens of thousands, right, that are connected to each other. And that's why, well, this is the reason why we have things connected, assuming you have cache coherence, of course, right? Okay, so I will not go into this detail, but whatever I described applies. An example mechanism looks like this. For each cache block in memory, you store p+1 bits in the directory, and that's costly. Now imagine doing a calculation of this. What's the size of the directory? If you, P is the number of processors that you have in the system. If you have tens of terabytes of memory, if you have cache blocks of 64 bytes, you divide 10 terabytes by 64 bytes and multiply by p+1. That's the number of bits you have in the directory. That's actually a lot larger than your caches, actually, in fact. Okay, but assume that you have it somehow. You have 1 bit for each cache, indicating whether the block is in the cache, that local cache or local processor. In this case, processor and cache can be used interchangeably because we're assuming a processor is a private cache. And we also have another bit, exclusive bit, saying that a cache whose bit is set has the only copy of the block and can update it without notifying others. So there could be optimizations that you can do, basically. This directory can grant permission to a cache that requested to update a cache block, saying that, okay, you have the cache block, you can update it until I take away your permission. And you don't need to notify me while you're updating this, because I guarantee that no other cache has this block, right? So basically, you can do a lot of interesting optimizations with directories. So on a read, the directory, the cache sends a message to the directory, and the directory sets the cache's bit in the directory entry for the block and arranges the supply of the block into the cache. If it was updated by some other processor, for example, it takes the data block from that processor and gives it to the processor that's reading it, right? And on the write, the directory makes sure that it invalidates the block in all caches that have the block and resets the bits of those caches in the directory entry for the block, because it's going to give the cache block to someone so that someone can update it, right? And we have an exclusive bit associated with each cache block in local caches so that the cache can know to update the exclusive block silently without notifying the directory. So if it got permission for this cache block from the directory, it sets its bit called the exclusive bit in the tag store, saying that, oh, I'm accessing this block and the exclusive bit is set, which means that I know now that I'm the only cache that has the copy in the system, and I can silently update it without going through the directory, okay? Or I can read it also without going through the directory, right? Okay, make sense? So now you know the two basic coherence methods. It's important to know, I think, this much. If you want to know about optimizations, you'll have to take the future courses. And this is, for example, the state machine for each cache block that's implemented in Pentium Pro processor. It's called the MESI protocol. The protocol that I showed you was valid-invalid. Actually, with the directory, we looked at an exclusive bit. MESI is, there are 4 bits, basically 4 states: invalid state, exclusive state, shared state, and modified state for each cache block, basically. Exclusive means basically I have the only copy of the cache block, so I can write to it. Okay, and there are a lot of other things over here, but we don't really have time to talk about those.